doing? Doing? pieces of a broken puzzle. By 1915 he called it continental drift. It caused a rift with his fellow scientists who sang, Alfred Wegener, you are a crazy man. Alfred Wegener, you are a crazy little man. They reminded him he had no proof for how or why the continents could do this. And until you show just how or why, you merely have one interesting hypothesis. Until this evidence we see, you don't have a theory. Alfred Wegener, you are a crazy man. Alfred Wegener, you are a crazy little man. In the year of 1930, on an expedition to Greenland, Wegener got caught in a blizzard. When they finally found him, it was much too late, and they buried him in an icy mausoleum. 30 years after he died, a new idea came to light. It changed the way geologists saw the world and brought continental drift back to life. Now everybody sings, yeehaw! Alfred Wegener, you are a brilliant man. Yeehaw! Alfred Wegener, you are a brilliant, brilliant man. Continental drift, Alfred Wegener's theory, continental drift. Alfred Wegener's theory, continental drift. Alfred Wegener's theory, continental drift. Alfred Wegener's brilliant.
We can call for help? We gotta reboot the system first. door locks! Ellie, boot up the door locks!
It's a unit system. I know this. It's all the files of the whole park. It tells you everything. I gotta find the right file. Oh, this is it. This might be the right file.
I don't want you on this game right now.
What are you talking about?
You've been on kill 'em up games all day and all yesterday.
It's because my new favorite game.
I don't like it. You know.
This isn't the right file. This might be the right file. This isn't the right file. This might be the right file.
I was laying in my bed last night thinking about that, bro. Like, if I just, like, took a shovel and I just started to dig into my grass, I wonder when I'd hit the ocean, bro.
This isn't the right file. This might be the right file. This isn't the right file. You got it! Yes!
Dinosaurs lived a long time ago. They were terrible lizards, don't you know? Some ate plants, some ate meat, some ate fish, and some ate beets. Well, hello everybody, and welcome back to Paleontologizing. Glad you could make it today. We've got a special stream planned because today is a special day. Before we get into that, let me introduce myself to any new folks who might happen to be here for the very first time. We're starting a little bit early today, as we often do on Wednesdays. So I don't know if there's anybody new here, but if there is, an extra special welcome to you new folks. My name is Danny Anduza. I'm a dinosaur paleontologist. You probably are already aware that a paleontologist is a fossil scientist. I work on dinosaur fossils in particular. That's what I publish on in the scientific literature. That's what I study. That's what I excavate during the summers. I excavate dinosaurs. This past summer, I was working in western Wyoming and eastern Utah, digging up dinosaurs live on stream, actually. We're able to live stream our excavations, digging up at least 3 new species of dinosaur. You should check out the YouTube page if you weren't here to catch that live. And if you were, well, I hope you enjoyed it. It's such a privilege to be able to do that kind of science outreach. I think that was pretty special. When I'm not in the field, I'm here in my office. Talking about fossil science, talking about natural history, talking about how we as scientists learn about the natural world. And most of what I'm doing is answering your questions about it, chat. So if you have any questions about dinosaurs, because that's what I actually study, or about other fossil critters, from, fossil insects to plants to whatever, or if you have questions about natural history in general, the history of life on Earth, the fossil record, extinction, evolution, the philosophy of science, any of that good stuff, don't be shy with those questions, and I hope you stick around. I hope you learn something here. Welcome to Paleontologizing. Before I go through and say hello to everybody in chat, let me tell you what we're talking about today, in case you didn't read the stream title. Today happens to be the birthday of Alfred Wegener. born November 1st. (1880). Holy cow. Alfred Wegener is often called the father of continental drift. We'll be talking about his legacy today. We'll be talking about his ideas. We'll be talking about how he died before his ideas were accepted by the scientific community. But he was vindicated in spectacular fashion years later as different branches of science converged upon this idea that the Earth's continents are not fixed in place, they actually move over time. It is today one of the best accepted ideas in science and most well supported. We'll talk about why, and we'll talk about why it took so long to catch on. It's going to be a fun stream. But before we go to that, let's say hello to everybody in chat and do some greetings here. Science Streams, you were indeed first today. Welcome, welcome, Valente. I hope you're having a great day. It's good to see you. Atuday was second. How you doing, Atuday? Hello, hello. Glad you could make it. And we've got Arle. How you doing, Arle? Welcome, welcome. Golganek. What's shaking with you, Golganek? It's always lovely to see you. I'm glad you could be here today. We're gonna have a fun one today. Otto the Potato. What is shaking with you? And what kind of unholy amalgam have you made of those dinosaur emotes? A ceratopsian body with a baryonyx anterior portion, arms and neck and head. That's will haunt my nightmares. Out of the Potato. Welcome. And Hugh Fun, how are you doing, Hugh Fun? Welcome back. Glad you could be here. Andy Then Did, hello, hello. Tommy Plodicus, welcome, welcome. I'm glad those of you who were here liked my choice of music at the beginning. Kind of a cheeky choice of tunes with, who was that? Was that Carole King? It's almost like she was singing about continental drift. Sparky Pugwash, welcome, welcome. It's good to have you here. And Golganek, I'm glad you like the new starting soon screen. Yeah, I just made that this morning. We'll be alternating between the previous one and that new one. And maybe some additional new ones, too. Especially as I get ready to move into a new office. Lots of new stuff on the horizon. Haraz, how are you doing? Welcome, welcome. Bruce Lee, what's shaking with you? I'm glad you could be here. And Claire Burr. Howdy, howdy, Claire. I'm glad you could make it too. I hope you're having a good day, Claire. Grim Deviant. Hello, hello. Welcome back. A Truck Horn. Lovely to see you as it always is. I dig those dancing geckos. Those are good. Little Pink Pony. I'm glad you like the Alfred Wegener song too. That was a good one. We'll share that in a little bit after some more people come in too. Lots and lots of videos and things to discuss, and we've got some book passages and all kinds of good stuff to cover on today's stream. Matt M33, a Tradoon to you too. Welcome, welcome. Orchestran, glad you could be here today. Kodali, hello, hello. Chris TS, welcome back. Witch Hannah, hello to you also. Hugin, what's shaking? We're not going to talk about the dinosauromorphs. Yeah, we'll be talking about dinosaurs a little bit. We always talk about dinosaurs here. Yeah. We'll be talking about dinosaurs a bit. Volcano Doc, how are you doing, Volcano Doc? Holy cow. In looking for clips today for our broadcast, Volcano Doc, I happened upon some really, really cool old documentaries about volcanology. Let me know if you'd like me to give you some links to those. But they were neat, from like the 70s, I think. With kind of, I don't know how you would describe that. It was like 70s lounge music in the background. It was fun stuff. But let me know and I'll give you those links. Ash Rubber, how are you doing? Welcome, welcome. Spectre Flight, thanks for the lurk. Glad you could make it too. Sandwich Nom Nom, hello, hello, Sandwich. Welcome. C Films says, have you seen The Night at the Museum movies? I've seen the first one, I think. Yeah, I don't really remember much from them, though, to be honest. I don't know if they had a big effect on me. And Ash Rubber, we're going to be doing a Dinosaur Deep Dive-a-thon tomorrow. So feel free to redeem that now, and we'll cover it tomorrow if that's good with you, Ash Rubber. Yeah. And Ben, theme park enthusiast, how are you doing? Welcome, welcome, Ben. Howdy, howdy. Are you enthusiastic about theme parks? I'm glad you could be here today. Jenny Lack says, what did you do with Danny? You're not the one I saw on screen yesterday. Oh, very funny. With the Ceratosaurus costume. Yeah, that skull is now back on the shelf. Yeah. But yeah. And G. Shumway says the Alfred Wegener Institute is one of the most renowned institutes about climate and ocean science in Germany. Yes, I mean, Alfred Wegener was, by trade, a meteorologist, but intensely interested in geography and oceanography. And one of the books that we're going to be looking at today, written by Alfred Wegener, is called The Origin of Continents and Oceans. Yeah. So Wegener, one of the greatest German scientists of all time, by many counts. Yeah. And Wegener may be cool and all, but Marie Tharp is way cooler, in my opinion, says Volcano Duck. We'll be talking about her a little bit, too. Yeah. She helped to actually accumulate some of this information about continental drift. Because apparently she wasn't really allowed to go out and do field work, just on account of being a woman. Frustrating. But she managed to make some incredible contributions nonetheless. Actually, if you have any really cool videos about her, I would, that would be really cool, actually. I don't have a video specifically about Marie Tharp, but if you could recommend one, Volcano Doc, we'll show it. Yeah. And, yeah. When you're enthusiastic about dinosaurs, too, Ben, theme park enthusiast, well, good, you were in the right place. Welcome, welcome. Go for Fluff or Not, hello to you. Welcome back. Yeah, and, where was that? I think it was here. Nope, it wasn't that one. Give me a second, Volcano Duck, and let me find some of those links for you. Let's see here. Well, there we go. Here is a YouTube channel that had a bunch of different earth science documentaries there, Volcano Duck, including some cool ones on volcanology. Earth Science Docs X. There you go. Yeah, heartbeat of a volcano monitoring the Mauna Ulu eruption. Volcano, birth of a mountain. The rock cycle, a review of the origin of rocks, and etc. There's some good stuff. I was looking for stock footage for some new cold open videos in the future, and those popped up. So, yeah, enjoy, Volcano Doc. I was thinking of you. Yeah. But yeah. And, it is Wednesday already. Who was saying that? It just jumped around. Hello, Espy. Welcome. Yeah. C Films wants to know, do I have a favorite museum? I've got a few museums that are very near and dear to my heart. C Films. We can run through them real quick if you'd like to. Some images. The University of California Museum of Paleontology in Berkeley, just down the road from me. I was here yesterday. This is kind of where I started as a larval paleontologist. When I was in high school, I volunteered at UCMP at Berkeley. And, yeah, that was where I got my start. After that, Worked at Museum of the Rockies. This is actually the same Tyrannosaurus skeleton out front. Museum of the Rockies. The Wonkel Rex. Yeah. Worked there, did field work there. This is kind of where I learned to be a dinosaur paleontologist. Was in Bozeman, Montana. And then other favorite museums. Carter County Museum in Ekalaka, Montana. I've helped out here before. This is where the annual Dino Shindig is. Every summer. Very cool, tiny little museum in a tiny, tiny town in eastern Montana. Ekalaka, Montana. The Carter County Museum. Cool place. Also, the Badlands Dinosaur Museum in Dickinson, North Dakota. I've done work here as well. And it is, again, one of my favorite places. Some of the exhibits that I worked on and stuff like that are here at the museum in Dickinson, North Dakota. So yeah, there's 4 museums for you. There's a lot more that I'm very fond of, but those are really the big 4 that I've actually contributed to. I've never been to the Terrell yet. Not yet, SB. Someday. Yeah. Anyway. Yeah. And G. Shumway says the African continent started to develop fault lines. Oh yeah, there's a big rift valley. Pretty famous in East Africa. Guess we won't see the continent breaking apart in our lifetime, but the process has started. Yes, indeed. A similar sort of thing is happening right now in the Basin and Range province in the United States. Nevada in particular. So what's happening right here in the Basin and Range province, there you go, is that there is a split that is occurring. This area is rifting apart slowly, year by year. And eventually, you'll have an ocean in the middle of Nevada. Because all of this is being extended here. Sorry, that's so small. But yeah, being rifted apart like that. And there's actually a really neat segment at the end of a book that we're going to look at today. Basin and Range, where the author accompanying a geologist across Nevada visits all these different geological sites, and then the book closes up with the author talking to just regular folks in a small Nevada town. So I think it was the barber and volunteer firemen and woman who runs the drugstore, and just saying yeah, eventually one of these days Nevada's going to be an ocean millions of years into the future. And just collecting these people's thoughts about it is really funny. It's well, I guess it'd be pretty nice to have beachfront property. Stuff like that. It was charming. Yeah. Anyway, that's going to be millions of years in the future, though. And buy your cheap waterfront property now. There you go, Solid Schmaltz. Welcome to Paleontologizing. It's good to have you here. Anyway. And G. Shumway says, was in California/Nevada last year, but didn't find time to visit the San Andreas fault line. I did a live stream from the Hayward fault line in Berkeley, California, a couple years ago. It actually runs directly through the University of California, Berkeley campus. In fact, it runs immediately through the football stadium. They have, with incredible foresight, they've decided to name it in advance Memorial Stadium. I guess in case the big one happens to hit during game day. Yeah, but that's the fault line running right through Memorial Stadium there. And live on stream, we actually looked at the Hayward Fault. There's two big bricks that, it's on this end of the stadium. There's like the, what do they call it? The proscenium arch? That's what it's called in theater. I don't know what it's called in sports. But the, like, you know, tunnel archway thing that the players run out from onto the field. There's two bricks there, and one of them is offset by like 6 inches. And that's because, you know, one side of the stadium is moving north, and the other side of the stadium is moving south. It's pretty cool, actually. Yeah. And, yep, you can see the cracks on the stairway there. The exterior wall on the north side of the stadium. And then the north tunnel. Yeah, there's N echelon cracks right there. Which are characteristic of fault creep. And yeah, this was even more dramatic when I went to go see it. But these are offset. Which is pretty cool. Yeah. Anyway, if you want to read more about that, here is a link. Yeah. And Parker Zilla says, to my mind, the key was exploration and advances in surveying, which resulted in a more or less accurate map of the world. And the natural fitting of the jigsaw pieces is apparent. I think it was the start. We'll be talking about that, yeah. Because, of course, once again, what we are discussing today is continental drift. This is the idea that the continents are not fixed in place, but they slowly move over time, year by year. And with enough time, that very slow movement, but the same rate at which your fingernails grow, can cause massive changes. The way that the continents move and the shapes that they create has tremendous implications for life on Earth, for climate, for the biogeography of different organisms. It's one of those big keys to the puzzle for really understanding the history of life on our planet. It's understanding continental drift. So this sort of thing is immensely important for, say, you know, a dinosaur paleontologist to understand. Because the different dinosaurs that we have on different continents are explained in part by continental drift. It's really cool stuff. It's why the dinosaurs at the beginning of the age of dinosaurs are all relatively similar to one another. It's that, and also, you know, they'd recently diverged, so they all shared a common ancestor very recently, so they tend to look pretty similar. But you get the same dinosaurs basically in North America and in Southern Africa, because at that time you could walk from one landmass to the other, and they did. Oh yeah. Yeah. Anyway, yeah. And Ji Shumway says, who thought it was a good idea to build $1 million stadium there? Who thought it was a good idea to have college sports? Is an equally valid question. They're, you know, an enormous drain on the college system, on higher education in general. College sports are such a scam at every single level. But don't get me started on that. Yeah. It's just par for the course. Yeah. Anyway. Yeah. But let's take a look at this. You might recognize the narrator in this first little video here. Kind of set the stage for today's broadcast for the birthday of Alfred Wegener. Let's start with this.
Germany, 1911. A meteorologist named Alfred Wegener was browsing through some books when something caught his eye. A list of identical plant and animal fossils that had been found on opposite sides of the Atlantic Ocean. Wegener was intrigued. How could the same species have gotten from one part of the world to another? He examined the eastern coast of South America and the western coast of Africa, and was struck how the shapes of the two coastlines might fit together. The more he looked, the more links he found. Species of land mammals in East Africa also inhabited the island of Madagascar.
Mm-hmm.
How did that happen? Did the animals evolve in both places at once? Or did they somehow cross from one land to the other, swimming hundreds of miles across the Indian Ocean? And then Wegener saw it all clearly. He realized that all the continents in the world had once formed a giant single landmass that he called Pangaea, from the Greek Pangaea, meaning all Earth.
Yep.
It was in Pangaea that the plants and animals found on opposite sides of the world had once...
All in this one afternoon in the library. Exactly, Solid Schmelz. I mean, for the sake of dramatism, they had to simplify it a bit, but no, this was, I'm sure, an idea that took a long time to develop. And Liz Aaron, thank you for the follow. Welcome to Paleontologizing. It's good to have you here.
shared the same home.
Lumpland.
Then, over hundreds of millions of years, Pangaea had split apart, and its jigsaw pieces had drifted to their present locations. Wegener called his theory continental drift.
And Solid Schmaltz, thank you for the Prime sub there. I appreciate that very much.
If they're removed, America loses them forever.
Thank you for that support. I know it doesn't cost you anything as a Prime sub, but it means a great deal to me, so thank you for helping keep me here on the air. Thanks for supporting Science Outreach on Twitch. Good stuff.
Wegener wasn't the first scientist to speculate that the Earth had once been dominated by a supercontinent, but he was the first to pull together all the evidence and make a strong case for it. Unfortunately, his peers weren't very receptive.
Nope.
There was no mechanism to explain how the continents might plow through the oceans. Continental drift was just too incredible to believe.
Which, makes sense at the time. The thing is, in science, we need mechanistic explanations for things. You can have a handful of observations that, like, wow, it really looks like these continents fit together like pieces of a puzzle. And, it's interesting that these plants and animal fossils from different continents look very similar to one another. Despite being separated by huge, vast oceans. But without like an underlying mechanistic explanation for how the continents can move, it doesn't really work as a scientific idea, And in Wegener's time, people didn't really understand much about how the Earth actually worked. And so, searching for some sort of mechanistic explanation for it, Wegener stumbled there. And of course, he ended up dying before his time. Which is probably one of the reasons why the whole idea kind of stalled out. Until it was later rediscovered by new scientists with new methods of studying the Earth. One of these themes that we're going to be encountering again and again today, one of the things I'm going to be repeating at least, is that science is constantly changing and we're always coming up with new ideas, finding new ways to test old ideas, challenging old assumptions. Science progresses, it marches forward. That's what it does. And an idea might seem outlandish at first, and that could either be because it's not true, or it could be because we don't yet have evidence that supports it. If an idea is actually true, if something is the way that the Earth actually works, the way that nature actually proceeds, eventually it'll come out. Eventually it can be demonstrated. This is one of the ways in which science is different from like other ways of knowing. It's different from opinion or conjecture or philosophy or religion. In science, we test things. And we're ruthless about it. You know, by our nature as scientists, that's how science works. And so if an idea has any truth to it, eventually somebody will figure that out. That's exactly what happened with Continental Drift. Oh yeah, yeah. Because until you tharp, you can't Wegener. There you go, Golganek. Yes. Yeah. Yeah. And Patrick Crusader. Wow, big earthquake in Sweden? Interesting. Sweden's not known for its earthquakes. Earthquakes are something that make a lot more sense now that we actually understand the mechanism behind them. Plate tectonics. Yeah. Anyway. Hugen says, look how long it took for extinction to take hold in science. Yeah. Well, science hadn't really been around for that long before the idea of extinction came to the fore, you know, around the turn of the 19th century. Yeah, around 1800. Yeah, I mean, science had kind of been in its infancy before that. At least from my perspective. Shoot, paleontology and geology are fairly recent sciences. Other sciences like physics go back to the time of, like, you know, Isaac Newton or earlier. But, you know, those are the easy sciences. The simple stuff. Once you start building up those layers of complexity, you know, from physics into chemistry, into applied chemistry like geology, and then kind of applied geology in paleontology. Paleontology being a mixture of geology and biology. Yeah, it gets more complex. Trickier to understand. Yeah. But yeah. Anyway, and yeah, no. And Tiny Toxitofu says physics, easy science. I mean, not easy per se, but simple. And I don't mean that in a way that denigrates physics at all. I'm just saying that by its very nature, physics is dealing with the most basic building blocks of the universe. You have the fewest levels of complexity when you get down to the very particles that make up everything. Does that make sense? The more layers of complexity that you add, the more complicated things become. And the trickier it is to hold different variables constant, like we do in the sciences. That's what science is all about. And I like to bring this point up because I know a lot of people, especially in physics, like to act all hoity-toity about their science. Like, oh, well, look it up. We're physicists, and physics truly is the queen of the sciences. It's the most scientific of the sciences, and that's kind of a fundamental misunderstanding of the philosophy of science. There's a wonderful book about this that I'd like to shout out real quick. You can get it as an audiobook, too, and I was listening to it again as I drove down to TwitchCon a couple weeks ago. It's got kind of a weird title, but the book is Nonsense on Stilts, How to Tell Science from Bunk. I think the editor may have chosen the title, because it doesn't really describe what the book is about. The book is kind of an exploration of the philosophy of science. What science is, what's the difference between science and between things like philosophy, and what's the difference between science and pseudoscience? What is a scientist's role in society? And how do we best reach out to the public? It's a really excellent book. I'd highly recommend it. But one of the ideas in there is that this whole, like, dichotomy between supposed hard and soft sciences, it's not at all a dichotomy. What it is basically like a gradient of it's a spectrum between simple sciences and more complex sciences. Simple sciences like physics, And again, I don't mean simple as a denigration here. I just mean that it's kind of at its most basic. It is as basic as you can get in the sciences, is physics. Because you're dealing with the tiniest things. I know physicists really don't like to hear this kind of thing, but yeah. Anyway. Yeah, Inidrex says geology is to physics as chemistry is to physics. I mean, geology is kind of applied chemistry and applied physics. That's an oversimplification to say that, but yeah. Yeah. And as social science talked about in the book, it is indeed see films along that same spectrum. So social science, often called like a soft science. Physicists really love to rag on social science and say, well, you know, that's not actual science because, you know, you're not running calculations or stuff like that. I don't know. But the funny thing is, when you look at meta-studies that have been done about reproducibility in different sciences, reproducibility meaning like being able to replicate findings across different laboratories. Like 2 different groups studying the same thing, they run the same experiment, do they get the same result? In the social sciences, their reproducibility is generally the same or even sometimes better than in physics. So if reproducibility is a mark of good science, which I think we can agree it would be, at least that is consistent with good science, you know, as a way to define that, then yeah, social sciences often rank pretty high. So yeah. Parkerzilla says some things can't be accurately reduced to some numbers, and this is true. Yeah, that's why social sciences, it's, they generally have other ways of trying to replicate findings. Let me see here, if I can find this. Right here. Hard science, soft science. I don't know if I'm going to be able to find this in time. But it's basically in chapter 1 of this book, so if you want to check it out, it's right there toward the beginning. Yeah. On the other hand, we have a second continuum from sciences that deal with simple, highly tractable systems, like physics, where one can apply strong inferential methods, physics, chemistry, to sciences dealing with extremely complex objects, where statistical treatment is often necessary, and where the ability to explain and predict phenomena is much reduced. Things like evolutionary biology and human psychology. All these differences have nothing to do with the quality of the intellectual endeavors themselves, and even less to do with the intelligence or brilliance of the participating scientists. We will now move to the even trickier consideration of the number of disciplines to definitely bring us out of mainstream science. Yeah, anyway. So that's like, it's transitioning into the next chapter. Sorry, I chose kind of a bad paragraph to read there. Anyway, we're getting a little far afield there. And so, unless I find it in the next minute or so, we're going to move on. Yeah. Anyway, yeah. Let's see. Through chat. Reproducibility is relative. Agreed, Haraz, yeah. But anyway. Good stuff. Here we go. Talking with Volcano Doc earlier, like you saw, and I stumbled across some old, cool documentaries. This was one of them, and I'd like to share it with you. This is from 1970, I believe. This is when continental drift was still a fairly new idea. This is during the ongoing scientific revolution in which continental drift was starting to be taken seriously by people like geologists. And I think this is a pretty lovely, from what I've seen, the first bit of this, pretty lovely kind of summation of where the science stood at the time. And it has only progressed since then. So, let's go ahead and dive into that.
The idea of continents drifting about the globe is as old as the idea of flights to the moon, and until recently, equally laughable. But Earth scientists have been getting very excited about some new discoveries in geology and geophysics. To begin with, what is the evidence for continental drift? Professor Sir Edward Bullard explains the geometry.
And looking at this at first, I'm like, what is up with this super crude globe right here? What's going on with this? Like, this is something that an actual scientist is using? These are pretty crude shapes, and then you'll see why it makes sense in a minute.
Most people must have noticed that the coast of Africa is a very similar shape to the coast of South America. It was pointed out ages ago by Francis Bacon in the time of James I, but no one took the thing very seriously until Alfred Wegener, a polar explorer,
whose birthday is today, November 1st, 1880. Holy cow. That's why we're having this stream today for anybody who just waltzed in.
Just before the First War, suggested that once
World War I is what he means.
Had fitted together
See?
Like the pieces of a jigsaw puzzle.
They're magnetic. They slide around.
In fact, they do fit really rather well. You get little gaps. In fact, I think the gaps on this model are probably bigger than the gaps in nature. There is a trick in fitting
Very
them
funny,
together.
Mayor Space.
That is that you've got to fit them at the real edge of the continent. The real edge of the continent is not the shoreline. It's the place where the shallow sea changes suddenly into the deep ocean.
So basically, continental crust versus oceanic crust here. We'll talk about the distinction between those later.
There's a bit of sea here, but this is all shallow sea.
Is this a great prop? See, can you It's wonderful.
Is the real edge of the continent. Now, you can do this fitting in the rest of the Atlantic.
Oh, yeah.
You can put, if you're clever enough to fit it in, you can put Greenland in there, and you can bring North America across and fit it on. You've got to be a little careful with Spain. Spain has to be turned round a bit. This is about the only cheat there is in the thing. And then these two together will come round like this, and really the jigsaw puzzle pretty well goes.
Wow, you've got Pangea.
If you have a jigsaw puzzle, not only have the bits got to fit together, but the picture ought to fit together too. And it really does fit together excellently. And up here, this lot of rocks in this area are 2,000 million years old. And then there's quite a sharp line.
2 billion years.
And then here...
I like how he says that. 2,000 million. I guess nowadays people are maybe a little bit more familiar with the idea of a billion. After 1970. I wonder if there were any billionaires in the world in 1970 yet. There were, of course, several billion people. Probably about 2 or 3 billion people on Earth. 1970, something like that. Yeah.
There are rocks which are 500 million years old. Well, now, if you take this line between the two and go across this very narrow gap into Brazil, then you come out in a little village called, I think, San Luis here. And it's a wonderful thing, but the rocks at the western end of the village of San Luis are 2,000 million years old.
That makes sense, Jim. It does.
And the rocks at the other end of the village
Charlie's Dragon. You're right.
Years old, like these. The pattern.
I like that. Yeah, 500 million or 2,000 million. It is easier to make that connection there, so maybe that's why he did that.
Really does continue across.
The pattern in other parts of the world can be more tenuous, but if you place Australia fairly close to India, there are certain geological contours, minerals and so on, which would seem to link the two continents together.
Yep.
But it's not only rock formations that leave traces for scientists to look at. In the study of fossils, paleontologists have always been keen enthusiasts for the drift theory. And
oh yeah, yeah. This is the thing, is that, like, in paleontology, the idea of continental drift was taken more seriously than it was in, you know, circles of geographers or geologists sometimes. Paleontologists are oftentimes at the forefront of scientific revolutions. We have been a few times in the past. There haven't been that many big scientific revolutions in the past 200 years, but things like evolution, well, holy cow. Paleontologists were all over that from the beginning because it helped explain some of the weird things that we saw. It fit with the observations that we were making about nature. It was a model that helped explain and predict what we would find in the fossil record. And those predictions came true, you know? Same with continental drift, where we've got weird fossils that show up in South America and in Africa, you know, on opposite ends of the Atlantic Ocean, and they're identical. Creatures that could not swim all the way across the ocean, you know. Organisms like plants. We've got the same fossil plants in both of those places. Yeah.
Dinosaurs do provide evidence.
An animal such as this little dinosaur here, Coelophysis, will do very well. You can see from the hind limbs that Coelophysis was a little fast-running dinosaur. We know Coelophysis from some deposits in Arizona and also in Rhodesia. So one way or another, he could get around the world between those two continents.
Rhodesia there is Zimbabwe. That's what that country is today. Yeah, Rhodesia is really charged term. Zimbabwe is that country's name. Yeah.
Coelophysis from some deposits in Arizona.
Good old Coelophysis.
So one way or another, he could get around the world between those two continents.
Nowadays, we recognize that those dinosaurs from Zimbabwe aren't Coelophysis per se, but they're a Coelophysoid. They're a closely related animal. Yeah.
And so could a lot of the other big dinosaurs which lived in the world with him. Unfortunately, we don't know the route by which they could get from one place to the other. Today, of course, you can't get across the Bering Straits. But in those days, there are many reasons for believing that the Bering Straits region was much warmer than it is today, and also that there was dry land there. So all of these dinosaurs, for example, those that were living in North America, could have spread across the Bering Straits into Asia and then on down into Africa. In fact, Lystrosaurus is probably the best evidence from the vertebrates of continental drift.
So this is an animal that's not a dinosaur, but if you've seen the new Netflix series Life on Our Planet, if you've watched that, you're probably well acquainted with Lystrosaurus. I think they feature that critter a lot because Lystrosaurus is one of those animals that makes it through the Permian mass extinction, the Great Dying at the end of the Permian and the beginning of the Mesozoic era. Lystrosaurus makes it across that and kind of takes over the world afterward. It's one of the lucky survivors. It's not a dinosaur, but Lystrosaurus is an animal that's much more closely related to the mammals, like you and me. Lystrosaurus. There is a close-up of that critter. There's multiple different species of this animal, but it is a mammal relative. Yeah. And they managed to survive the Permian mass extinction, and then the world was their oyster at the beginning of the Triassic. They spread out all across the globe, and they could only do that if the continents were mushed together. These are not the sort of animal where, you know, they're going to be able to swim across the modern Atlantic Ocean. Not a shot. Not a chance. They had to have walked. And walk they did.
Now, we've known this little reptile from deposits in South Africa and China and in India for quite a long time. This is a skull, which I think shows its structure quite clearly, as the lower jaw down here, rather a downturned snout, the nostrils and the eyes. Now, the important fact was the discovery of this animal.
And it wasn't in Walking with Dinosaurs, Charlie's Dragon. That's Placerius that you're thinking of, which is kind of the last member of this group. So Placerius is it is a relative of Lystrosaurus. Yeah. Well, it looked like this in Walking with Dinosaurs. It's also a Dicynodont. It's a member of the same group as Lystrosaurus. But Placerius is like the last one, or one of the very last of them. Lystrosaurus is from the very, very beginning of the Triassic period, just after the Permian mass extinction. It made it through the Permian mass extinction. Placerius is like the last of the line before the dinosaurs really take over at the beginning of the Jurassic. Yeah. So yeah. So, good thinking, Charlie's Dragon. Yeah, there's an actual connection there. Yeah. Anyway. Let's continue.
In Antarctica only last December. This is a skull, which I think shows its structure quite clearly, as the lower jaw down here, rather a downturned snout, the nostrils and the eyes. Now, the important fact was the discovery of this animal in Antarctica only last December. Now, for Lystrosaurus to have got to Antarctica and to have survived there implies, I think, such different positions of the continents and climatic conditions in the continents that surely continental drift is the only reasonable explanation.
Yep. So again, this is so cool that we're watching this. This is from 1970, when this idea was still being hotly debated. It was not established science yet. This is something that was a matter of you know, lots of arguments at scientific conferences at the time. It's pretty cool. It's pretty cool.
In fact, the study of weather in prehistoric times, paleoclimatology, has shown that certain parts of the world have undergone extreme changes in temperature and climate. England, for example, must have been nearer the equator.
Yeah.
We have here a typical well-rounded desert sandstone, typical of the Sahara today, and yet we're now in this bleak part of Durham. And this sandstone, which is about 250 million years old, gives you excellent method of determining the direction of east in the past. You can see from the dunes here that the wind direction must have been blowing these grains up and down over the dune. So from this you can work out the wind direction.
That's pretty cool.
At that time the wind was blowing from the east across here. And yet today it is quite clearly in this direction. So quite clearly Britain must have rotated relative to the pole since that time.
In the southern...
I mean, this is a wonderful example, I think. This whole documentary here and the whole idea of continental drift, our whole topic today is, I think, a beautiful illustration of how geology really is like detective work. You're looking at this physical evidence, trying to figure out how it got there. You're looking at the rocks and the earth itself. If you study it really, really hard, it kind of reveals the story to you. Real Sugar says science is so cool it hurts. I know, right? Yeah, earth science rocks, literally. I agree, Fiery Faye. I'm glad you're here. Kennedy says Tokyo drift? Well, Tokyo has certainly drifted over the years, along with every other place on our planet. Let's continue.
Atmosphere. Glaciated rocks of the Permian age were recently found as far north as India.
Yeah, nuts.
One reconstructs what might have been the South Polar ice cap at that time, the implications are fairly startling.
Yep. Pretty neat. And again, you gotta love how back in the 70s they're able to still, you know, have these really cool graphics without CG or even animation. They obviously had animation, you know, like cell animation back in the 1970s, but just with a physical model, you could do some really, really cool stuff. So you kind of gotta love that. I know I like it.
Ice cap at that time,
yeah.
The implications are fairly startling.
Physical effects, yeah, Charlie's Dragon.
Even so, All the evidence so far was only an indication and not actual proof of continental drift.
True.
During the last decade, the science of paleomagnetism has transformed the picture.
This is really cool stuff. Is anybody here familiar with paleomag at all? This is something that dinosaur paleontologists talk about, especially when we're talking about stratigraphy and trying to figure out exactly when a certain dinosaur had lived. Paleomag can be one of the best tools in our arsenal for figuring that out. And he then did says it's news to me. Oh, this is super cool. This is going to blow your mind. Check it out.
This solid wall of rock began life in liquid state some 300 million years ago. As it welled up to the surface from the interior of the Earth, it cooled, solidified, and became magnetized by the Earth's magnetic field.
So the Earth has got a magnetic field around it. I'm showing this to you. They might show you on the screen in a minute during the documentary, but the reason why compasses and things like that work is because Earth itself has a magnetic field. Janie, thank you for the follow. Welcome, welcome. We've got a North Pole and a South Pole. There's magnetic North and magnetic South. Well, here's the thing. Over the course of Earth history, over millions of years, sometimes the poles flip. Magnetic South becomes magnetic North and vice versa. And so imagine you had like a compass in your hand and a time machine. You know, you take a picture of the compass in the present day with north pointing north. Then you go back, say, 1 million years when the poles had flipped. And you take a picture of it, and now south is pointing north, even though you're standing in the same exact spot, in the same position. It's because those magnetic poles flip. The cool thing is, there are magnetic particles within igneous rocks. So like when lava cools, there are magnetic particles in that, bits of iron and stuff like that. And they will align with magnetic north and south in the rock. And they'll cool there, they'll get stuck there, frozen. And then maybe the poles later shift, but they're still frozen like that. And so if you can find magnetic material inside of igneous rock from a long time ago, you can actually figure out, like, oh shoot, the poles were flipped back then. And you can basically create a time chart, like it flipped here, and here, and here, and here, and here. And then you can line it up and figure out how old it is based on that. It's super cool stuff. Nessie Gaia, thank you for the follow. Welcome to Paleontologizing. Thanks for joining us. Yeah. And Harasses, it's still unclear as far as I know why the pole flips. I'm not sure if we really understand that well. Yeah. Here. Let's continue this. See if they talk about it.
This magnetization will remain frozen in the rock until it returns to a liquid state.
Mm-hmm. And how often do they flip? There's not like it's not like a set number of years and it flips every set number of years. You can go long times when it's magnetic normal and then you get reversals. And we can actually look at that in stuff like, let's see. Do they talk about it here? Let's see. Linear time. Some geologic timescales will actually have magnetic normal or magnetic reversal. Here we go. Beautiful. Yeah, geomagnetic polarity timescale. So say you want to go back to the end of the Cretaceous period, the Maastrichtian, the very end of the Age of Dinosaurs. We've got this black and white on here. I'm not sure which is which. I want to say white is normal and black is reversed, but it could be the other way around. So anyway, but you get long spans of normal, and then a reversal, and then a long span of normal again, or vice versa. And I don't know if it's particularly well understood why those magnetic pole flips happen. But yeah, it has happened a lot, MLF. Yeah. And Oscar Jr. says black is normal based on current color. Okay. Yeah. So yeah, pretty neat. And is it just the magnetism that changes, or does the whole planet turn upside down? No, it's literally just the magnetic polarity changes. Like it can do with a magnet. Like you can screw up a magnet if you put other magnets nearby it. I think you can actually like change the polarity of the magnet if you like mess it up. I know I've accidentally broken compasses like that before when I was a kid, like, you know, putting a magnet next to it and like watching the needle follow it around. And sometimes you do that too much and it's like, shoot, now south is pointing north permanently. And you have to try and break it back. Yeah. I don't know why it happens like that on the Earth, but it does. Let's look that up real quick. Let's see here. Let's try this on SciShow, perhaps.
Every once in a while, Earth's magnetic field weakens to almost nothing, flips north for south, and then bulks back up again. In fact, this happens somewhat regularly.
Wow, he's got long hair.
Heard that we're due for a flip-flop with catastrophic consequences, which isn't really true. But you
It's
may
not
have
true,
also heard that nobody knows why they happen. That is a little truer. Fortunately, geophysicists have made huge steps in understanding why our normally calm magnetic field sometimes goes haywire. Let's start by going over the basics. Beneath our feet is the Earth's crust. Below that is the mantle.
And G Cubed says approximately every 300,000 years it flips. I mean, not really. That's the thing, is that you can have huge periods where it stays the same for like tens of millions of years. And then you've got times when, you know, when it flips really rapidly back and forth. So maybe more recently there's kind of an average times, but not really. It almost seems kind of random. Yeah, so don't think that it happens like on a regular schedule, because it definitely doesn't.
Then the outer core, then finally the inner core. Most of our magnetic field comes from iron in the outer core moving as the planet spins. As electric charges in the iron move, they create a magnetic field around them, making Earth into a big bar magnet with magnetic south on top and magnetic north on the bottom. And yes, that means right now it's the opposite of what you'd expect, though it doesn't actually matter in the scheme of things. This is known as the dynamo theory, and it's really the only game in town for explaining Earth's magnetic field. But it's hard to study the outer core directly because it's obscured by crust and mantle. And changes down there can take millions of years, which is time we just don't have to work with. So scientists have to get clever. Measuring the current field really carefully can give us some hints about what's going on down there. And while scientists have found that the field has gotten weaker in the last couple of centuries, don't get nervous just yet, because they can also look at ancient volcanic rocks. As lava solidifies, bits of iron in the lava,
what we were just talking about,
magnetic field around them like tiny little compasses. So volcanic rocks lock in the field that existed when they first froze. Scientists started systematically looking at these magnetic fossils in the 1950s, and right away they noticed that magnetically, Earth's crust is striped like a tiger. In some eras, the north magnetic pole pointed south like it does today. In others, it pointed north. Line up the ages of those rocks and it shows that over our long history, the magnetic field has reversed hundreds of times. There's still debate over how long it takes for the planet to undergo a full reversal, but it seems that over a few thousand years, the field will get weaker, then briefly go away almost entirely, and then get stronger again in the opposite direction. On average, this happens every few 100,000 years or so.
Interesting. I mean, apparently NASA said the same thing, like G Cubed said. On average, this happens every few 100,000 years or so. I mean, from the perspective of a dinosaur paleontologist, it's like we had huge periods of normal polarity within like the Aptian and Albian stages of the Cretaceous. And that was far from every 300,000 years that it was changing. Maybe it's like if you take this random pattern and then average it out, it would be every 300,000 years or something like that. But that kind of makes it sound like it's more regular than it is, you know?
Dinosaurs were the sort of creatures you
Ironheart.
might think of as inhabiting another planet.
Holy cow, Ironheart
The
50.
kind you dream of in a bad nightmare.
40 months to support 40. 40. 40 months. That's almost a whole year, Ironheart. I appreciate you. Almost enough time for a pole reversal.
But there's a lot of variation around that average. The field
There we
might
go.
flip a
Yeah.
bunch of times within a few million years.
Okay.
Or it might be stable for tens of millions of years.
Okay, thank
It doesn't
you.
really come due to flip given the amount of variation.
Okay,
Measurements
nice,
show that the field
nice.
today is about as strong as it was in the middle of one of those really long gaps with no reversals. There's no reason to expect one coming soon to an Earth near you. But measurements alone can't tell us why the field flips in the first place. For that, geophysicists turn to computers. One of the going hypotheses is that reversals are tied to plate tectonics. Specifically,
Exactly what we're talking about today, everybody. This is awesome.
plate subducts or gets shoved under another and then drifts down into the depths. The idea is that when the remains of an ancient plate reach the boundary between the core and the mantle, it changes how heat transfers between the layers, which in turn affects how iron moves in the core. A problem with this hypothesis has always been that nobody knows how long it takes for a plate to descend through 3,000 kilometers of the mantle after subducting up here on the surface. Some calculations lead to estimates of around 30 million years. Others say it's closer to 300 million. And since
That's
we don't
only an
know,
order
it's
of
hard to
magnitude.
look for patterns between field flipping and subduction throughout Earth's history. But in 2018, a team of scientists approached the problem from the opposite direction. Instead of calculating the delay first, they started by looking at subduction and magnetic field reversals throughout geologic time. They were looking for a consistent pattern where there was a lot of subduction, then a certain delay, then a lot of field flips. And they found that lots of reversals tend to happen around 120 million years after periods with a lot of subduction. And those really long periods without reversals tended to be about 120 million years after periods with very little subduction.
So there's a 120 million year delay after a lot of subduction or little subduction, and then you get a pole flip. That's the idea. Wow. Interesting.
Simulations have shown that once the remains of a plate reach the bottom of the mantle, it can change how heat escapes from the core, which changes how iron moves around the outer core. And research has also shown that when iron in the outer core is disrupted, small variations in the behavior of iron between the core and the mantle can have a big effect on whether or not a reversal happens. So it makes sense that even in periods with lots of flips, it's not like one happens every 500,000 years. There's some randomness in what happens with the iron at the boundary. Measurements have also shown that even between field reversals, periods with lots of them tend to have weaker fields on average, which again makes sense if the heat flow between the core and the mantle is a key factor. If there's not enough time to build up a strong field before heat flow gets disrupted again, it's easier to break down the field and lead to a flip. Once, scientists wondered whether something as big as an asteroid was necessary to set off a magnetic field reversal, but the science is increasingly clear. Earth's tummy can do flips all on its own.
Pretty cool. Here's a link to this video here. There you go. Yeah. So what does that have to say about continental drift? How is magnetic pole reversal evidence for this in the 1970s?
Will remain frozen in the rock until it returns to a liquid state.
Ooh, power tools. They're gonna do a core, aren't they? Yeah.
These scientists are taking a sample of the rock so that they can measure the direction of the magnetism. One might imagine that the magnetism in samples from all over the world would all point north-south. The answer is they don't.
Yep.
Rocks of different ages from different places point to different north poles. But there's only one north pole, and as it stays more or less in the same place in relation to the sun, it's therefore the rock samples that have moved.
Pretty cool. It's like detective work.
If the samples have moved, then so have the continents. So how do we find out exactly where they were?
This is a model of the Earth's magnetic field as we see it at the moment. It can be well represented by that which would arise from a large magnet buried at the center of the Earth, and the lines of force come out from the region
I
of
love
the
these
South Pole
physical models.
and go in.
Oh, these are great.
The North Pole. And the compass needles on this frame follow the direction of this magnetic field at the Earth's surface. A rock forming on the equator now would acquire a magnetization parallel with the Earth's surface, and at some intermediate latitude, such as England, it would acquire a magnetization dipping about 66 degrees into the ground. And one forming at the pole would
these models. I know, isn't that cool, Zucchini Puff? I love it.
Into the Earth. Well, the direction of magnetization in this rock is nearly horizontal, and this means that either England was here when it was formed and has acquired this horizontal magnetization, or if the magnetic pole was in the Pacific in those days, then we see that the magnetic field in England was horizontal. Either way, this means that when this rock was formed, England was in equatorial regions relative to the pole in those days.
Pretty
and this is what
cool.
paleomagnetism is all about. We can estimate the ancient position of continents by measuring the direction of magnetization from rocks within them.
This is really, really neat. So this same model, like this model right here that shows that like old England, according to this model, according to these findings, would have been mostly equatorial at the time. You can cross-check that with other lines of evidence. And so you can go and you can look in those same rocks from that same time period and look at what the plants look like in those rocks. What kind of environment do those plants hint at? And holy cow, the plants from the Cretaceous of England are they're subtropical or tropical plants near to the equator. Pretty cool stuff, right? Pretty cool stuff. Fiery Face says we would have been like the Bahamas back in the UK, I guess. I mean, shoot. England in the Cretaceous would have been much warmer than today. This is an old illustration, really old Iguanodon and Polacanthus, Hypsilophodon. But this is the kind of environment you had back then. And then earlier in the Jurassic, England looked
Tradoon.
very different also. There we go. There you go. That's Oxfordshire during the Jurassic. Pretty cool, right? Pretty cool. Yeah. We now know these guys couldn't actually come up on land. They were fully adapted to life in the sea. But yeah, like the Bahamas. Fire Faye, yep. Yeah. Where did they actually film that, though? Let's see. Cruel Sea, Walking with Dinosaurs, filming location. Third episode in the Walking with Dinosaurs series. The episode was mainly advised by David Martell. Filming locations are New Caledonia and the Bahamas. There you go. Yeah. Pretty cool. Pretty cool. And those animals probably could not sunbathe on the land. No, we think that they were fully aquatic nowadays. the Cryptocleidos, those plesiosaurs that you see there, these guys would not actually have come up onto land at all, we think. We used to think they had to have come up onto land, because how else would they lay their eggs? Nowadays, we recognize these animals actually did not lay eggs at all. We found fossils of these guys with embryos inside, like basically a fetus inside that showed us that they gave birth to live young in the water. Just like dolphins do today. Or whales, or sea lions, or whoever else. So we don't think they came up on land at all anymore. They, yeah. They didn't lay eggs, they gave birth to live young. Pretty cool, right? Pretty cool. Anyway, yeah. And Chatty Lex says, why is the movie mirrored? So that YouTube doesn't freak out and copyright strike it when I put it up on YouTube later. Or rather, when Claire takes some time to push some buttons to make sure that it shows up on YouTube. Thank you, Claire, for doing that. You know I appreciate you. And it seems to be helping? Good. Anything to make it easier for you, Claire. Good stuff. Yeah. Anyway, let's continue with this old documentary about continental drift here.
By measuring the direction of magnetization from rocks within them.
At Newcastle University.
And thank you, Captain Saar, for the follow. Welcome, welcome. Good to have you here.
Found it simpler to work out where the poles appeared to be and to plot a polar wandering curve. The first man to do the field work for this was the man who's now Professor of Physics, Professor Runcorn.
The Earth is a gyroscope, and the gyroscopic effects due to its rotation not only keep the axis of rotation fixed in space, but also control the generation of the Earth's magnetic field, so that the magnetic pole, on average, coincides with the geographical pole. Some years ago, I examined the directions of magnetization of rocks from the top to the bottom of the Grand Canyon, which cover 1,000 million years. The results form a rather simple pattern.
Somebody has some questions about reptile eggs versus fish eggs and stuff. Emily says, how do fishes lay eggs? So fish eggs are water soluble. They're like water can permeate them, and they don't drown. Whereas you take a reptile egg and you throw it in some water, like a chicken egg, like you'll kill the embryo, you'll drown it, because it's got a hard shell to it. Does that make sense? So fishes lay their eggs underwater. Thank you there, Star Knight, for helping clarify there. Yeah. And the Devonverse, how are you doing? Welcome. Welcome. Yeah. Yeah.
The pole appears to move, as viewed from North America, in an arc around the North Pacific. The surprising result, which came out of this work, was that the polar wandering path from America was about 25 degrees west of the polar wandering path derived from rocks from Europe.
Huh.
This was the fundamental paleomagnetic evidence for the drifting of the continents.
Pretty cool, pretty cool.
If the polar wandering curves for rocks from South America and South Africa are brought together so that they match, not only are the two continents brought together, but the curves show the moment at which the two continents started to drift apart.
I love these physical models. These are so cool. I've never seen anything like this before. Oh man, that's neat.
The continents of the world are reconstructed for that date on paleomagnetic data alone. Then the South Pole is centered on about Johannesburg, while Britain was exactly on the equator.
Pretty cool. Pretty cool.
This means that with one sweep, paleomagnetism confirms all the previous evidence for continental drift.
That's so elegant. I love that. I love that. Yeah. Tanareem, how are you doing? Welcome, welcome. Good to have you here. Yeah. And Fiery Faces, I love that the UK was once on the equator. Isn't that cool? Yeah. Pretty neat.
Inevitably, the computer has played its part, and at the Atlas Computer Laboratory, the computer is able to produce on film a projection of the breakup of the southern hemisphere.
Lost ancient technique.
Notice how the other continents flee from Antarctica.
It's some more lost ancient tech right here, isn't it?
And at the Atlas Computer Laboratory, the computer is able to produce on film a projection of the breakup of the southern hemisphere.
This would have been cutting edge stuff at the time. This would have been, yeah. Oh man, gotta love a documentary from 1970. Yeah. And you remember that printer? Yeah, we had a dot matrix printer at my job when I worked at that auto parts store. Yeah. Wasn't even that long ago. That was like maybe 7 years ago. They probably still have it there. Shoot. Yeah.
Notice how the other continents flee from Antarctica, which seems to get stuck in the same place. This is a process which continues to this day. Watch it again, and this time look at India, the small triangle on the right, which hurls itself towards Asia.
Very cool.
Going further back in time, Australia has performed a sort of elephantine waltz with the South Pole as a partner.
Emma, it says 7 years ago. Where did you even get the paper? Apparently you could still get it. That, or they had maybe a whole closet full of it from the 80s. I don't know. But yeah. And this was still with the CRT monitors, the cathode ray tube monitors, where it's just like green text on a screen. We still use those. This is like less than a decade ago. Yeah. And Ben Theme Park Enthusiast says, fascinating how the UK was on the equator. I never knew that. Now you do. That's the beauty of continental drift, my friend. That's why we're talking about this. We've known about this stuff since the 1970s, and like, I really wish this were taught in schools more. But natural history is like severely undertaught. And honestly, it's like religious fundamentalists who fight to keep this thing out of the schools because they're threatened by it. But yeah, it's wondrous when you actually learn about it. This is really, really cool stuff. Look at Australia go. There you go, Christy. Yes, yeah.
Paleomagnetism will take us back to the age of the Earth itself. But for the moment, the best picture.
And have continents ever crossed the equator, or does the Coriolis effect ever hold sway over tectonic plates? No, no. The Coriolis effect doesn't really have anything to do with that. They'll cross the equator willy-nilly in aerospace. There's no holding those continents back. They do what they do. And our dog loves this music. Let's play it again, Solid Schmaltz.
Elephantine waltz with the South Pole as a partner.
There we go. Is this a waltz? Okay. Oh, that's great.
Eventually, paleomagnetism will take us back to the age of the Earth itself. But for the moment, the best picture comes from only a short time ago, when life began.
At this time, 300 million years ago, we had two supercontinents, something like this. The northern one called
Laurasia. Oh, yeah.
And Gondwana land in the south.
We just talked about Gondwana the other day.
Ocean, which is known as the Tethys. Now, these continents, the northern continents, were made up of North America and Europe.
And I don't think he's trying to draw the Pog Komodo dragon here, real sugar. Looks like Pac-Man, says Tannerim. Well, this is a really simplified drawing of Laurasia and Gondwana. So, nowadays, you know, it would look like this. Yeah. Does that make sense? Up top in Laurasia, you've got North America, and you've got Europe and Asia. Laurasia. Down below in Gondwana, the southern continents, you've got South America, Africa, Madagascar, India, Antarctica, and Oceania. Australia. So he simplified it a good deal here. About as much as you could. But, yeah. Yeah.
And Asia, the southern continents had Africa in approximately this position, with South America attached to it.
Civ 6 still uses
India,
the Very cool, Christy. Yes, that's neat.
Australia and New Guinea, approximately here, and Antarctica around here, and
there we
New
go.
Zealand across here.
But if this was the Earth 300 million years ago, what was round the other side?
And
well,
that wasn't the Earth 300 million years ago. Well, I guess maybe it kind of was before it comes together as Pangea and then breaks up again. But I would say this is the Earth about, 160 million years ago. It would have looked like this. Yeah.
Suggestion is that the world used to be much smaller.
And when you look at things more closely, you find that the continental jigsaw puzzle can be done on this smaller Earth rather nicely.
This isn't going to be the expanding Earth hypothesis, is it? Because that was still something that some people held to in the early 1970s. Let's see where they go with this. This is a super outdated idea. It's been really dramatically disproven. But let's see this here.
Now, naturally, as the Earth slowly expanded after this, the skin had to crack, and it did so around the borders of the Pacific Ocean. That is, around here and here on this smaller globe.
Really, really funny. Holy cow, that's great. So, it's crazy to think that as recently as the 1970s, there were still people who seriously held to this idea. The idea that the Earth is expanding and expanding and expanding. And that's why the continents broke apart. It might seem like a really, really far-fetched idea, but, well, nowadays it is, because we know better. Nowadays, yeah, here, this is from a really excellent podcast called Skeptoid. Today, of course, the notion that the Earth got into its present configuration by expanding from a smaller size seems silly. It seems to belong to with the flat earthers and the hollow earthers and all the other geophysical crackpots. But how would you react if I told you that expansionism was actually a mainstream theory and not all that long ago? And further, if I told you that contractionism, its opposite model, enjoyed a similar mainstream status. As recently as 1900, contractionism was in fact the leading model of the Earth's geodynamics, with expansionism a close second. Mobilism, an umbrella term for theories like continental drift, and eventually plate tectonics, was considered the realm of crackpots then. So it turns out that a skeptical look at the expanding Earth theory, and as we'll see in its day it did indeed qualify as a theory, it's not just a case of poking fun at nutty YouTube channels. So there's a pretty good little primer on this here. Yeah. Nowadays we recognize that this is a ridiculous notion that the Earth has been expanding, and that's why the continents look like they fit together like puzzle pieces. But at the time, before anybody really knew much that was true or useful about the way that the Earth works, it was a plausible kind of idea. So you can check that out there. It's good stuff. Yeah. Haraz says, what do they think would replace the missing mass while the Earth expands? I don't know, Haraz. I don't know. I don't know if they ever got that far with the idea. Yeah. Anyway. Yeah. So I guess this guy is advocating for this idea right here? Or is he not? Maybe he's just trying to show what people thought? I don't know. Sometimes it's a little bit difficult for me to follow these videos while I'm also trying to keep up with chat, but
Well,
Yeah.
ideas naturally are rather speculative about this.
Yeah.
And I think this will keep us busy for at least the rest of my lifetime.
And how long was that, by the way? Who's this guy? Let's look him up.
Used to be much smaller.
And when you look at things more closely, you find that the continental jigsaw puzzle...
I want this guy's name so we can...
Smaller Earth.
Professor Ken Creer of Newcastle. Let's see. Kenneth Midworth Creer, Professor of Geophysics at the University of Edinburgh.
This. And I think this will keep us busy for at least the rest of my lifetime.
So the rest of his lifetime was until 2020, right here. August 19th, 2020. And yeah, he was maybe a little too optimistic about that because by about the late 1980s, continental drift was pretty much universally accepted by geologists the world over. There were very, very few holdouts, maybe bordering on zero by the end of the 1980s. And nowadays, continental drift, tectonic plates, these ideas are some of the best supported in all of science. So, universally accepted nowadays. Yeah.
So, the evidence for continental drift seems unassailable. But it still leaves wide open the question of how such massive journeys were possible. How do you move thousands of square miles of solid rock such long distances?
How do you move solid rock?
And what about the ocean floor
over vast
in between?
distances?
Since the war, oceanographic surveys have revealed huge mountain chains on land, running continuously through the Atlantic, Indian and Pacific Oceans.
These are the spreading ridges.
Did the continent slide across the sea floor and over the mountains? The skeptics, quite rightly, said this was impossible, and it wasn't until paleomagnetism went to sea that an answer began to emerge.
Oh yeah.
Two
Oh, this is good
unrelated
stuff.
discoveries were waiting for a catalyst to link them up. The first was the strange phenomenon of polarity reversals.
We already suspected when we started on this work that the polarity of the Earth's magnetic field had changed. Well, that sounds like a very complicated thing, but what I mean by it is this, that at the present time, the Earth's magnetic field is pointing north. We mean that in the past it was pointing to the south much of the time, to the north. It switched back and forth. And the problem for us was to find out when these north-south switches had occurred. What we had to find in order to do this was some sort of a natural tape recorder that could give us a record going back many millions of years. We found our tape recorders, and this is what they looked like.
Every time a volcano erupts, a new layer of molten lava is spread down the mountainside on top of the previous one.
Yep.
Each layer has the Earth's magnetic field locked in it from the moment it cools. And where the sea has eroded away the mountain, the layers are exposed.
We made measurements working our way down the cliff, found the uppermost lava flow was magnetized to the north, the second one, and then we would find the next lower one would be magnetized to the south. And at this exact point, we knew that we had captured a reversal of the magnetic field. We did this in many parts of the world. And when we put it all together, we had a detailed time history of the field, which I've sketched over here. We found that there was a long time when the field had been pointing to the north, and then 800,000 years ago, let's say, it was
just like those charts that I was showing you earlier.
This way, we were able to build up a very detailed history of north-south switches going back, something like 3.5 million years.
Nowadays, we've got this same kind of chart for much of Earth history. Right here. So geomatic polarity timescale, this goes all the way back to the beginning of the Cambrian period. So we've got a really, really good idea of all of the pole reversals that have taken place up until 540 million years ago. That's pretty extraordinary, I think. Isn't that cool? Yeah.
Going back, something like 3.5 million years.
The other discovery was even more curious. The US Navy allowed a British scientist, Professor Ronald Mason, to tow a magnetometer behind one of their survey ships in the Northwest Pacific in order to measure the pull of gravity over the sea floor. The map they produced showed clear stripes.
Hey, Lucid Dream, welcome.
And sometimes
Good to have you
thousands
here.
of miles long, which
And latest Kate
alternate
was shaken.
strengths and weaknesses in the magnetic properties of the sea floor. But geologists could make nothing of them, and they remained a mystery.
And Pendrake says, how long until the next one? What triggers the flip? We talked about that a few minutes ago. We watched a whole video on it. So I'm not going to retrace my steps that much, but check it out. Those pole reversals seem to happen at fairly random intervals. At least it's not like on a set schedule or anything, so we don't know how long until the next one. Yeah.
For about 10 years.
Yeah.
The mystery was finally solved
This is
when
super
the
cool.
polarity reversal timescale was applied to the magnetic stripes by Fred Vine, one of two Cambridge geologists, who produced a revolutionary new theory.
Very cool. So again, we're talking about Alfred Wegener today because it's the birthday of Alfred Wegener, born November 1st, 1880, but his idea of continental drift was never accepted during his lifetime by, most Earth scientists. It would take the work of hundreds of other researchers, like this guy here, in order to help demonstrate that, yes, this is the real deal. Yes, that idea fits with the evidence. Because that's the thing about science, is that for an idea to be well accepted, it has to fit with the evidence. That's how science differs from other ways of knowing about the world. Other ways where, like philosophy or religion or other things like that, sometimes you try and fit the evidence to your idea. In science, your idea has to fit with the evidence, because we're actually studying reality, the natural world. Yeah.
Yes, the concept was first formulated in some detail by the late Professor Harry Hess of this department. And he made this simple, rather elegant suggestion, although rather startling at that time, that the oceanic crust, that seafloor is continuously being created at mid-ocean ridge crests, such as the crest of the mid-Atlantic ridge here in the South Atlantic. It is generated above an upwelling in the mantle and spreads laterally away from the crests, thereby drifting the continents apart as though
And Ken's here too. How you doing, Ken? Welcome. Good to see you.
So I might represent this, therefore, by a simple Mickey Mouse model, such as this, illustrating the way in which the conveyor belt
That's not Mickey Mouse.
crust and upper mantle material flows out from this central crack in the Earth's
Seafloor spreading. I love that. Before, complex computer models, before all kinds of fancy graphics like that, sometimes you just use a pair of scissors or a razor blade and a newspaper.
illustrating the way in which the conveyor belt of oceanic crust and upper mantle material flows out from this central crack in the Earth's crust.
Pretty cool. Yeah.
Now, in 1963, Drum Matthews and myself, then at Cambridge,
Sparky Pogwatch says, I think he has not seen Mickey Mouse before. I'm sure he has. Mickey Mouse just means that, like, something is ad hoc or unserious or kind of rinky-dink, Like, I've used that term before, where I've talked about, like, real paleontological expeditions where you're excavating fossils versus, rinky-dink Mickey Mouse pay-to-dig operations.
Present this, therefore, by a simple Mickey Mouse model, such as this.
Does that make sense? Yeah.
Well, now, in 1963, Drum Matthews and myself, then at Cambridge, added the simple rider to this, and in effect converted his conveyor belt of oceanic crust into a tape recorder. We suggested that as new crust is formed, solidifies,
at a ridge crest. Frozen into it will be the current direction of the Earth's magnetic field. This will be subsequently moved aside as newer material.
Wreaking his prehistoric fury on modern man and his puny machines.
Mama Mabel, thank you for the follow. Welcome to Paleontologizing. Appreciate you clicking that follow button.
Material comes in. And in this way, successive avenues of crust, normally and reversely magnetized, will be built up, paralleling the ridge crest.
Super cool.
Symmetrically disposed about it. And indeed, going back to the anomaly map, the very detailed contour map of Ratham Mason for this area of the Northeast Pacific, and after peering at it for some time, we could see that indeed there is a remarkable symmetry of the magnetic anomalies about the crest of this so-called Juan de Fuca ridge in this area, and they do indeed reproduce all the details of the reversal timescale in remarkable detail.
Little Pink Pony says, Danny, do you think scientists in 2023 are more open to accepting new ideas? It depends on what those ideas are, Little Pink Pony. That's the thing. In science, there are lots of different ideas, and some of them might seem like crackpot ideas at first. So you kind of got to sit and wait to see which ones are actually supported by the evidence. Continental drift seemed like kind of a crazy idea at first, that the continents themselves, the Earth moves. The continents themselves drift around. This was, seemed like a far-fetched idea. But other explanations seem really far-fetched too, that the Earth is actually expanding or contracting. So you kind of got to sit tight as a member of the public and just, you know, realize that sometimes these things take time. If you're trying to get to the right answer, as scientists are, well, you got to be careful about it, and you got to really do it right. That sort of thing takes time. So are scientists today more open to new ideas? It depends what those ideas are. It's always going to be a case-by-case thing. Yeah. Yeah. Anyway. Yeah.
So to summarize this then, we drew up this new colored summary map, which emphasizes this symmetry about the ridge crests in a truly remarkable way. It's incredible to think that it had been in the literature for 4 or 5 years and people hadn't recognized the symmetry.
An aerial survey of a...
And sometimes stuff like that happens, where something will just be staring you in the face for a long time. It'll be staring the whole scientific community in the face, and sometimes it takes a while for somebody to recognize it. Not somebody. Usually it's like a group of people. That's another thing in science, is that it's very, very rare for there to be some lone genius in a lab somewhere who goes, you know, this is bizarre, but I have a eureka moment and suddenly I see everything clearly. Like, I know that idea gets a lot of attention in popular media. You know, that eureka moment, you know? Like, yeah, here. Let me show you. This lovely atlas right here. We've got an example of that. Let's see. Where was it? We're looking for Ecuador. South America, Brazil, Argentina, Bolivia, Chile, Uruguay, Peru, Ecuador. It was, of course, on islands off the coast of Ecuador that old Chucky D had a eureka moment, as the story goes. So, Galapagos, the birthplace of evolution. And thank you, Izkabul. Appreciate the follow. Welcome, welcome. Located 600 miles west of Ecuador, the Galapagos Islands are home to a vast array of unique species, as well as the tree that Charles Darwin was sitting under when a monkey fell on his head, giving them the idea for evolution. We all know the story. But it turns out in reality, it was actually a lot more complicated than that. At the same time that old Chucky D, in real life, no joke, at the same time that he was coming up with his idea for descent with modification by means of natural selection, what today we would call evolution, other scientists around the world were actively looking at the same problem and coming up with very similar ideas. Alfred Russel Wallace, a contemporary of Darwin, basically came up with the idea of natural selection on his own on the other side of the globe. And he actually wrote to Darwin and said, "Hey, what do you think about this idea? I've seen your work in natural history. What do you think about this idea?" And Charles Darwin was like, "Holy cow, I'm going to get scooped on this." And so they actually published a joint paper together. Because, yeah, Darwin knew that if he didn't publish his soon, somebody else was going to discover evolution first. So that's kind of what happened with continental drift, too. Alfred Wegener was sort of ahead of his time. It's rare that that happens, where he had this idea that the continents were, you know, in motion. But decades after his death, other scientists were kind of, maybe they were familiar with his work or maybe they weren't, but they kind of came upon the same idea, because that's the thing. If something is actually true, you should have multiple lines of evidence that show that, especially if it's something really big like continental drift. So yeah. And Random Bit says, what came first, the recognition of genetics or the theory of evolution? Ooh, that's a great question. But, and I have, I think I even have a clip about that. Let me see if I can find it. But it was definitely evolution that came first before anybody discovered DNA. Yeah. There we go. So, DNA and evolution. Here, this is from a wonderful documentary that we watched back in September about, like, kind of a court battle between science and pseudoscience. Science and intelligent design, which is itself just kind of a repackaging of creationist pseudoscience. But here's the little clip about genetics and evolution and how the discovery of genetics was a time in which, you know, the idea of evolution was really being tested. And if evolution weren't a real thing, it would have fallen apart with the discovery of DNA and genetic testing and stuff like that.
In the first place.
Yeah.
And therefore you could say that when modern genetics came into being, everything in Darwin's theory was at risk. Could have been overturned if it turned out that genetics contradicted the essential elements of evolutionary theory. But it didn't contradict them. It confirmed them in great detail.
Yep.
And as Miller would testify, a genetics paper published less than a year before the trial had confirmed what has long been the most inflammatory part of Darwin's theory, the common ancestry of humans and apes. That paper explored a curious discrepancy in our chromosomes.
So the reason that I'm showing this is it's again this idea of like scientific revolutions and like new ways of studying things help us test old ideas, and we kind of get ever closer to the way that things actually are. Different fields will converge upon the same, to use kind of a, you know, wishy-washy word, the same truths, you know? We'll arrive at the same truth, if it's true, with different modes of scientific inquiry, you know? They'll all reflect the same, you know, the same objective reality there. Patrick Pirate says, tag yourself, I'm a gibbon. There you go. Who would I be, Patch? Let's see. Mandrill, baboon, gibbon, bonobo. Let's see. Give me the red panda up there. Yeah. That's me, maybe. Or maybe I'm a rat. I don't know. What do you think I am, chat? There's no dinosaurs on here, unfortunately. Good stuff. Yeah, Ken says bonobo. I can see that, Ken. Yeah. Sociable. And a bonobo, they used to be called pygmy chimpanzees. It's a different species of chimpanzee that's very close to us. Here. Pull them up on the old Tree of Life. Let's jump to us on the great Tree of Life here. While we're talking about human descent. There we go. There's us. And what is our closest relative? It's the bonobo, which used to be... We used to just think that it was a subspecies of chimpanzee. Nowadays, they're their own legit species. Pan paniscus. And then there's Pan troglodytes, which is the chimpanzee. Right next to us on the Tree of Life. And then you go out a little bit more distant, you get to gorillas. And chimps, humans, and gorillas together form the clade African apes, homininae. And then the great apes. And I suppose they're pretty great, yeah. And then apes. And then old world monkeys and apes. You go further out. You get to monkeys and apes. Monkeys, apes, and tarsiers. And then primates. And then you can keep going out further. And you get to... bee and buggy, come on now. You get to Eucharonta, which is primates and things like prosimians like lemurs and tree shrews as well. And then you can keep going out further and further and further until you go all the way out to all life on Earth, which as far as we know came from a single common ancestor about 3.8 billion years ago. This is kind of the fundamental principle in all of biology, and without understanding that species change over time and they split and they beget new species, we wouldn't know of any of this stuff. So yeah, that was a big revolution in science. And yeah, there were many, many times when it all could have completely fallen over, like it could have just gotten burned to the ground if stuff like, you know, the discovery of DNA and genes, if that didn't confirm, you know, evolution, then shoot, we'd have to rethink everything. But the thing is, it fit perfectly with that because it's real, you know? Yeah. Here.
A genetics
of evolutionary theory, but it didn't contradict them. It confirmed them in great detail.
Yep.
And as Miller would testify, a genetics paper published less than a year before...
And Squiggles, please, I know what greater and lesser mean in biology. I was making a joke, trying to be facetious here, you know? I appreciate the urge to correct, but, you know, try and establish that I made a mistake before... Yeah.
The trial had confirmed what has long been the most inflammatory part of Darwin's theory, the common ancestry of humans and apes. That paper explored a curious discrepancy in our chromosomes. The cells of all great apes, like chimpanzees, gorillas, and orangutans, contain 24 pairs of chromosomes. If humans share a common ancestor with apes, you'd expect us to have the same number. But surprisingly, human cells contain only 23 pairs.
Weird.
The question...
Again, if you've ever, you've heard of 23andMe, right? That, like, genetics testing service? Some of you have probably done 23andMe testing before. That number, 23, is in reference to the 23 pairs of chromosomes. Which is weird because orangutans, gorillas, and chimps all have 24. And holy cow, Astro Canuck! Welcome, Astro Canuck. Holy cow. Astro Canuck, how did your stream go? I hope it was really, really good.
62 raiders have arrived to wreak some sweet havoc.
Welcome, welcome back to paleontologizing, Astro. Thank you so much for the raid. I appreciate that. By the way, it was wonderful to meet you at TwitchCon just a couple weeks ago. Yeah, what an honor to be able to meet you in person. Appreciate the science outreach that you do. Thanks for bringing your viewers here. Holy cow. And G-Monkey, A Poetic Side, Re-Dictator, Karen Is My Name, Dragon Boots, and Pyrax. How are you all doing? Welcome, welcome back to Paleontologizing. Welcome to Paleontologizing if it's your first time here. For some of you, I think it is. How are you doing? My name is Danny Anduza. I'm a dinosaur paleontologist. And I'm here on Twitch trying to do some good old-fashioned science outreach, just like Astro Connect does. As a dinosaur paleontologist, I study dinosaurs, I publish on them in the scientific literature, and I dig up dinosaurs. I was doing some live excavations on Twitch this past summer, working with the Utah Geological Survey, collecting specimens in Wyoming earlier for the Cincinnati Museum of Natural History. Yeah, nowadays, this is my full-time job, is doing science outreach here on Twitch. You caught us at kind of a weird time because we were going off on a big tangent about evolution. But we're kind of talking about scientific revolutions today. We're talking about big new ideas in science. Because today happens to be the birthday of Alfred Wegener, who is often called the father of continental drift. He was born on November 1st, 1880. And so we're talking all about continental drift today, and how this idea was not accepted during his lifetime, because he didn't really have all the evidence to back it up. Sometimes that happens in science. It was decades later that actually, you know, continental drift truly became accepted by geoscientists. Because, well, for part of it, the technology just wasn't there back in the 1930s. So yeah. Anyway. Thank you again for the raid, Astro Canuck. And can we get one more shout out for Astro Canuck? If anybody who was watching before the raid is not aware, Astro Canuck does astronomy and Lego building, and it's always a good time on Astro Canuck's channel. Some of the most polished special effects and on-screen graphics that I have seen, not just on Twitch, but anywhere on the entirety of the internet, on Astro Canuck's channel. So go give him a follow. It's always a good time. Yeah. Great to meet you too, Astro Canuck, my friend. Thanks for bringing your viewers in. This is great. Yeah. Here, since we've got a bunch of cool new people who just came in, why don't we do a little interlude with another video before we get into the main one that we were watching. Just to kind of bring the new viewers up to speed about continental drift, Alfred Wegener, all that stuff. G-Monkey.
Long and 14 feet high.
Thank you for that follow.
1,500 teeth and not a single cavity.
That's some excellent dental hygiene there, G-Monkey. Thank you for that follow. Let's get into it here. Quick video on Alfred Wegener and continental drift.
Just love it when you're right.
I'll try and get the correct subtitles going.
Of course you do. And so do scientists, though the scientific method makes us have to pretend like we aren't. Fact is, the whole of scientific history is filled with people who were totally right, and everybody thought they were wrong. And today I want to tell you about one of those people.
It has happened a few times.
The way that we look at the Earth. Alfred Wegener was born in 1880 in Germany. He was one of those rare people that's just good at and interested in a lot of different things. He got a degree in
kind of a polymath,
but went into the relatively young field of meteorology.
So, like Astro Canuck, intensely interested in astronomy from early on. Very, very cool. Very cool.
of different things. He got his degree in astronomy, but went into the relatively young field of meteorology, where he pioneered the use of balloons to track air currents and went on expeditions to Greenland to study polar weather, at which he was totally badass. He spent winters in a hut drilling ice cores, and he also made the longest crossing of Greenland's ice cap on foot for the win. But he was also interested in other stuff, including geophysics, which is why he got totally obsessed with this. He couldn't help but notice, like some school children will, that Africa and South
the biologist,
America
welcome.
look like puzzle pieces. Sure, they're thousands of miles apart, but they really look like they fit together. Of course, other people picked up on this. Like I said, you probably did around 4th grade. But another one of Wegener's great qualities is that he wasn't afraid to ask the stupid-sounding questions. So he just started asking people, continents moving, is that a thing? And if it was a thing, how would we know that it was a thing? And because he was a voraciously curious guy, he was looking for the answers to those questions in all kinds of places. And guess what? He found out that fossils of the same plant species had been found on both sides of the Atlantic. He discovered that the geology of the Appalachians was almost identical to that of the Scottish Highlands. And he learned that distinctive rock strata found in South Africa.
Oh, I could go into detail about all these things.
Almost as if the continents
But we want to get through this.
drifted. Finally, in 1914, while laid up in a military hospital bed during World War I, he pieced together his theory that all of the land masses on Earth used to be part of a single continent called the Ur-continent, or the origin of all continents. And over time, the masses moved, scattering fossils and rock patterns around the world.
Nowadays, we recognize that this is partially true. That Ur-continent was not actually the first continent. There have been a number of different supercontinents over Earth history, at least 3 or 4 that I can think of, that we know of. The continents are constantly moving and crashing into each other and then glancing past, and yeah, so there have been a number of times when there has been a supercontinent on Earth. It's not like it just happened one time. Pangaea was not the first one. That's only the most recent of the supercontinents. Yeah. And Lego Tegu, Pangaea is only the most recent one. We'll be talking about that.
Next year, he published his research in a book, The Origin of Continents and Oceans. And the scientific community...
And isn't this stuff cool, Dragon Boots? Yeah.
They totally freaked out on him. Geologists dismissed him as a glorified weatherman. They held entire conferences devoted to debunking his book. Even his father...
And
in-law, who was the most prestigious meteorologist in Germany, told him he should have probably stuck to the balloon thing. The convention...
Yeah, and shoot, I'm going to interrupt this video with another video because there's actually a music video about this, and I think you'll like it a lot. So, let me show you that. I think you'll appreciate this. Oh. And Tyler, thank you for the follow. Welcome, welcome. This is cool in the same way that Astro Canuck is cool, so Astro Canuck viewers, I think you'll appreciate this. I'm going to run to the bathroom while this is playing. I'll be right back.
In the year of 1910, there was a scientist whose name was Alfred Wegener. He noticed that the continents looked just like pieces of a broken puzzle. By 1915, he called it continental drift. It caused a rift with his fellow scientists who sang, ha ha, Alfred Wegener, you are a crazy man. Ha ha, Alfred Wegener, you are a crazy little man. They reminded him he had no proof for how or why the continents could do this. And until you show just how or why, you merely have one interesting hypothesis. Until this evidence we see, you don't have a theory. Ha ha, Alfred Wegener, you are a crazy man. Ha ha, Alfred Wegener, you are a crazy little man.
All right. Not bad, right?
too late, and they bury him in an icy mausoleum.
Yeah.
30 years after he died, a new idea came to light.
Plate tectonics. Yes, indeed.
It changed the way geologists saw the world.
It changed everything about geology, really. Not everything, but a lot. So there you go, Alfred Wegener. Born on this day, November 1st, 1880. Good stuff. So let's go ahead and get back into the other video right there, and then we'll get back into our main video that we were watching.
Traditional wisdom at the time was that continents used to be connected by land bridges that later collapsed or were covered by the oceans, and that's how they explain stuff like matching plant fossils. Of course, Wegener didn't do himself any favors by being actually pretty wrong about a lot of stuff. Like, he could not explain, he had no idea how the continent...
You should enjoy science as much as you can, and you can't enjoy science alone. You have to share it.
Bad Mandex, thank you for the 3 months of support. I really appreciate that. Thank you, thank you. And yeah, let me give you a link to that song by the Amoeba People there. Tea Time Cat. Claire Burr already posted the link a couple times, but there it is again for you. Yeah. Good stuff, right? Yeah. Yeah.
Actually drifted. He thought they were just plowing through the Earth's crust like an icebreaker. He also suggested that the centrifugal force of the Earth's rotation was causing the continents to drift, which is just totally kind of crazy. Yeah.
Let's protect our fossils, because if they're removed,
and
America loses them forever.
Chai Latte Nebula, thank you for subscribing there. I appreciate that very much. Thank you, thank you. Thank you for that pledge for ongoing support to Science Outreach on Twitch. I really appreciate that. Thanks for keeping me here on the air. These are some important points here. So, Alfred Wegener, the thing is, he had this idea that the continents moved, and he had accumulated some evidence of this, that it actually happened, but he didn't have a strong idea of any kind of mechanism. And part of this is that he wasn't actually a geologist. He was trained as a meteorologist, and his degree was in astronomy.
Soti Saint going well gifted a tier 1.
Soti Saint going well. Thank you for that sub gift there. I appreciate that very much. Look, we are halfway to our goal for the week, which is really nice. Yeah, about halfway through our, maybe a little bit more than halfway through our Wednesday stream. We're on track to make the goal this week, I think. That's excellent. Yeah, and we got Hype Train going. Beautiful. Thank you, Sothi, and thank you, Bad Mandex. Appreciate you. Yeah, so Alfred Wegener, he was right that the continents moved, but he wasn't right about how it happened. He didn't really understand that part, and the how of science is critically important. Just claiming that something happens, that's something, but actually having a mechanism for it is what really makes it kind of a scientific idea. And Wegener just didn't have that.
Not explain. He had no idea how the continents actually drifted. He thought they were just plowing through the Earth's crust like an icebreaker. He also suggested that the centrifugal force of the Earth's rotation was causing the continents to drift, which is just totally kind of crazy. Yeah, so the damage had been done.
The majority of people who do research in paleontology
and Lenina.
Be detectives in a sense.
You didn't have to do that, Lenina.
The joy of our field is
Holy
to
cow.
go out and put together clues that sometimes are extremely obscure.
Thank you, Lenina, for those 2 gift subs. I really appreciate that. Look, we're at 91 out of 175 now for the week. Excellent. Excellent. Thank you, Lenina. Good stuff. Had to nudge the I appreciate that, Lenina. Thank you very much. Yeah. Good stuff.
And everybody in Germany thought he was a total crazy person. No one would hire him to teach anywhere. The only job he could get was as a meteorology professor in Austria. And that is where he was in 1930, where he decided he wanted to go back to Greenland to set up some weather stations. And during a weeks-long excursion to bring supplies to one of these remote stations, Alfred Wegener disappeared in a blizzard. His body was found the following spring, and it is still there today, buried in the ice. I know, right? Because he was right. I mean, not about everything, but about a lot of stuff. And at the time of his
Yeah.
death, people were just starting to understand what the floor of the ocean actually looked like. And decades later, that research showed that there were giant rifts and mountain ranges under the oceans. And
Yep.
those were the boundaries.
Those are the plate boundaries.
Plates were pulling away
Yeah.
or crashing against each other. It wasn't until the 1960s that plate tectonics became something widely accepted by the scientific community. Though he wasn't vindicated during his lifetime, he is now respected as one of the greatest scientists of his era, and you can pay your respects to him through one of the many things in science that are now named after him, including the Alfred Wegener Institute for Polar and Marine Research, or the Wegener Peninsula of Greenland where he died, or craters on both the Moon and Mars. So, thanks here, Dr. Wegener. All of these fascinating things and more, we bring to you from SciShow, where you can subscribe.
Well, I'll give you a link to this video too. So yeah, that's why we're celebrating the birthday of Alfred Wegener. It's a wonderful opportunity not just to talk about continental drift, plate tectonics, the way that the continents move, why that's important, but also to talk about revolutions in science, new ideas, how scientific consensus actually forms in science among scientists. So yeah, and well.
The creature
Hello.
we will be examining is a paleontologist.
Thank you, Lordy, for the raid there. How was your stream, Lordy? I hope it was really good. Welcome back to Paleontologizing. Yeah. Tell me how the painting went, Lordy. I was able to catch the beginning of your stream. Looked like you were having some fun. I hope the painting went well, and more importantly, I hope you enjoyed the stream. Thanks for bringing your viewers here. Welcome back to Paleontologizing. Yeah. We are talking today about Alfred Wegener. There we go. Just the beginning of the song again. It's so catchy. I love it. Yeah.
1910 there was a scientist whose name was Alfred Wegener.
His birthday, today, November 1st.
He noticed that the continents looked just like pieces of a broken puzzle.
The song is a bop. I agree. And Fiery Faye, sleep well. I'll see you later. Thanks for being here.
With his fellow scientists who sang, Alfred Wegener, you are a crazy
I wonder if these are actually photographs of some of his contemporaries in Germany. Yeah. But, anyway. Spoiler alert, Wegener was right. That was true. Anyway, today we have proof of how and why the continents do this, and we'll continue on with this video here, talking about continental drift, and this is really, really cool because this is from 2026 there. This is from
the idea of continents drifting about
1970
is as old as the idea of flights to the moon, and until recently, equally laughable. But Earth scientists have been getting very excited about some new discoveries in geology and geophysics. To begin with, what is the evidence for continental drift? Professor Sir Edward Bullard explains the geometry.
The coast of Africa is a very similar shape to the coast of South America.
And watch how he demonstrates this. This is such a cool physical model here. I know it's a little thing, but I love it.
Alfred Wegener, a polar explorer, just before the First War, suggested that once the two had fitted together like the pieces of a jigsaw puzzle.
Yep.
And in fact, they do fit really rather well.
So anyway, it was kind of based on this simple observation at first that Alfred Wegener kind of had the genesis of this idea, and it has been confirmed by multiple branches of science at this point.
Ridge.
There we go.
Incredible to think that it had been in the literature for 4 or 5 years and people hadn't recognized the symmetry.
An aerial survey of a section of the mid-Atlantic ridge.
And the biologist says it's crazy to me how relatively shortly ago these discoveries were made. I mean, yeah. Sort of on that same front, there's so many things that we take for granted today ideas about how the world works that are fairly recent, like the idea of extinction, the idea that living things can go extinct. That idea has been accepted, you know, by scientists. Like, there's been evidence for that idea basically only since about 1800. Like, the scientific idea of the atom is older than the idea of extinction. Which is crazy to think about, right? We've known about the atom for longer than we've known that species can go extinct. So much of Earth science, including paleontology, as much as, you know, it's as much an Earth science as it is a biological science, these are fairly new fields. They're only a couple hundred years old. Geology, paleontology, honestly, biology. Biology only really became a, you know, scientific once we realized that creatures can change over time. You know, evolution is basically what turned, you know, zoology, biology into sciences. Botany, too. So, yeah. Confused Echidna, good to have you here. Welcome back. Thanks for returning. Good to see you again. Yeah. Anyway. And I guess science really isn't that old either. I know, right, MLF? I think about that sometimes, where, like, I don't know. I only recently have actually seen much Star Trek, but, you know, in Star Trek, set, you know, like 300 years into the future, a lot of that stuff's really not that far-fetched, given, you know, that most of our scientific fields now are fairly new. And if we continue to fund science and make new discoveries, a Star Trek future is honestly very possible in a lot of ways. And so much of society would seem quaint, antiquated, primitive by people in the future if we, you know, if we manage to get to that Star Trek point. That's the thing. Right now, in our current time, we're at an extremely important crossroads, you know? We've got basically, the way that I see it and the way that climate scientists see it, we've basically got like 10 years to make the choice between a Star Trek future and a Mad Max future, you know? It could go either way. We got to decide that right now as a species. And hey, Calamity, thank you for the follow. Welcome to Paleontologizing. It's good to have you here. Yeah. Anyway, you vote for Star Trek, please? Me too, Sparky Pugwash. Me too. Anyway, it's amazing how quickly scientific disciplines can advance and how they can improve all of our lives. Not just our understanding of the world that we live in and the universe that we call home, but, you know, improve our daily lives in the sense that, you know, advances in science mean improvements for medicine. It can mean improvements for society, how the way that we treat each other, you know, the way that we feed people. That I'm like sitting here thinking that I have to sell you on the virtues of science. I hope I don't. I hope you're already on board with that. But yeah.
An aerial survey of a section of the mid-Atlantic ridge produced the same magnetic stripes.
Yeah.
Still, there weren't many scientists who could accept the idea of seafloor spreading.
In '63, it was very frustrating because I had this idea and one realized that if it was true, you know, the implications were enormous. That the ocean basins were young.
Preaching to the choir. Yeah, I guess I kind of am a little bit.
All the oceanic crust, all the deep ocean basins that we see today.
Dr. Irrefutable says, so how did plate tectonics affect dinosaur science? Ooh. Well, that's the thing, is that, like we saw earlier, we're at 2056 right now, I know, so I can jump back to that. But yeah, paleontologists were kind of on board with the idea of plate tectonics or continental drift before people in other sciences.
But then on top of that,
Dino Wolf.
actually find the fossil makes the world of the dinosaur hunter
the world of the long shot.
Thank you, Dino Wolf, for those 6 months of support. Yeah, here, let me go back to this part of the documentary from earlier, just this little clip
Have
here.
always been keen enthusiasts.
Here we go.
In the study of fossils, paleontologists have always been keen enthusiasts for the drift theory. And certain dinosaurs do provide evidence.
An animal such as this little dinosaur here, Coelophysis, will do very well. You can see from the hind limbs that Coelophysis was a little fast-running dinosaur. We know Coelophysis from some deposits in Arizona and also in Rhodesia. So one way or another,
Zimbabwe
we get around
there.
the world between those two continents. And so could a lot of the other big dinosaurs which lived in the world with him. Unfortunately, we don't know the route by which they could get from one place to the other. Today, of course, you can't get across the Bering Straits. But in those days, there are many reasons for believing that the Bering Straits region was much warmer than it is today, and also that there was dry land there. So all of these dinosaurs, for example, those that were living in North America, could have spread across the Bering Straits into Asia and then on down into Africa. In fact...
Yep. And so, understanding continental drift and understanding what the continents are doing, suddenly so much of, like, biogeography of dinosaurs makes sense. And so that's really well intertwined with studying why different dinosaurs occur in certain places. Yeah.
Accept the idea of seafloor spreading.
In '63, it was very frustrating because I had this idea and one realized that if it was true, you know, the implications were enormous. That the ocean basins were young, ephemeral features, that all the oceanic crust, all the deep ocean basins that we see today were generated, say, within the past 200 million years of geologic time, less than 5% of the whole of geologic time.
Probably walked. There you go, Galrox, yeah.
Was it possible that the whole of the seafloor crust was so new? The question had to be answered. So, suddenly, the oceans of the world were busy with any craft the oceanographers and geologists could lay their hands on. The biggest was a specially built deep-sea drilling ship, the
Glomar Challenger. This is a legendary name in the annals of Earth science. Glomar Challenger. Ah. It evokes these images and feelings of scientific exploration and adventure on the high seas. Glomar Challenger.
Biggest was a
yes, indeed.
Deep-sea drilling ship, the Glomar Challenger.
Yeah.
Commissioned by the Joydes Group and based at the Scripps Institute of Oceanography in San Diego. This vessel must be one of the most expensive craft ever built for pure research.
Oh, beautiful.
6 engines hold it accurately on station while it drills in water several miles deep.
Gotta love it. You know, a vessel whose very purpose is to seek out new knowledge, to explore, to make discoveries that no one ever has before. Does that remind you of anything? To boldly go, Steely Dan? The Glomar Challenger. Its continuing mission. I don't know Star Trek that well, but so I can't fully recite it, but yeah. What an incredible vessel. That's the Glomar Explorer. Here's the Glomar Challenger here. Yeah. And you can even get t-shirts of it. It's that famous. Yeah. Pretty extraordinary vessel there. Good stuff. Did it have a 5-year journey? I'm not sure, Freelancer. Maybe. Nope, not 5 years. 15-year-long scientific expedition. Try 15 years. Yeah. Good stuff. They should make a TV show about that. That would actually be really cool, Patrick Crusader. That'd be really neat.
The object is to recover from the ocean bed a core of sediment representing millions of years of history, from the present day back down to the moment when the first layer of sediment
Not a 3-hour tour.
settled on the newly formed
Different
rock,
show, MLF.
and to see how old that first layer is. The ship drilled 2 sets of holes across the ridge in the North and South Atlantic, specifically to test the seafloor spreading theory.
This is tremendous.
Fast and Curious Continental Drift. There you go, Steely Dan, yeah.
Exciting because to a geologist, there's really nothing quite like a sample. You cannot determine the age of sediment, for example, from geophysical investigation.
Yep.
You have to have some of it in your hands. And in fact, by drilling all the way through the sediment layer and recovering not only the sediment just above the igneous rock, but in a number of cases, the actual igneous rock floor of the ocean.
Hey, Interstellar Desk Plant. Welcome, welcome.
Without exception.
Good to have you here.
That the
Thanks for joining us. Welcome to Paleontologizing.
Material did become progressively younger as one approached the crest of the rise system.
At the Lamont Geological Observatory at Columbia University are stored literally hundreds of cores from several different ships.
Yep. Shoot, when I was at in Utah this summer, I was based at the core lab at the Utah Geological Survey. And let's see, let's go back to October of last year. There we go. October. There we go. But there's a huge core research facility there. Here it is here. Here's Jim Kirkland and LJ Krumanacker here. And walking through the core facility. Every one of those boxes is a big core sample like that. It's just this enormous warehouse where they store all of these core samples. It's like this massive library or archive where geologists for a long time into the future hopefully will be able to come and study these samples that we're taking. Because it's not cheap to drill cores like that. So it makes sense to keep those samples around. So that's what you see there. Yeah. Jim, speaking of Star Trek, yeah, there you go, Claire. Yeah. Yeah.
These long strips of mud are priceless.
Yep.
1 millimeter can represent 1,000 years of history, and they contain enough information to dispel any doubts that the crust of the Earth has been moving and growing for millions of years.
Pretty cool. Pretty cool.
Seafloor spreading and continental drift are no longer a myth. They're fact.
Yep.
There's so much information coming in that scientists can now give us accurate dates as to when the continents separated.
We have been extrapolating both the anomaly pattern and the age outward from the ridge axis to the flanking basins and the continental margins. And from this, we've been able to suggest that that South America and Africa separated about 150 million years ago.
Yep, late Jurassic.
And this agrees reasonably well with the geologic information, which suggests that the first occurrence of marine sediments along the coast of South America was about 130 million years ago. In the North Atlantic, extrapolating again from the ridge axis using the magnetic anomaly pattern, we would propose that North America and Europe separated about 90 million years ago, and this agrees reasonably well with the...
It was actually a little bit longer ago than that, I think. But yeah, a lot of these dates have been refined since then with more information. Yeah.
Geologic
Thank you for the hydrate, no.
information.
Missed that 6 minutes.
This illustration shows the relative position of the continents about 75 million years ago.
Rothgar says, what was going on in the information hotspots that led to these geographic locations keeping the data so pure? I mean, they kind of don't. It's like, it's kind of everywhere, Rothgar. That's really the thing about Earth science, is that the evidence is out there, just in the crust of the Earth. Some places it's easier to get to, like with La Brea, that liquid asphalt, those tar deposits are just right there on the surface, basically. Sometimes those things are right there on the surface, and you can just basically pick them up, or just dig down a little bit in order to get them. You can find them there at the surface, With, like, seafloor spreading, it wasn't really possible to study that until you had the technology to be able to actually image the seafloor. It wasn't possible until after World War II. So yeah. It's, Earth science is cool because you can go just about anywhere on Earth and you can find interesting and important things to study. It's not like, these data are only available in certain places. If you're looking for maybe dinosaur fossils, then you have to go to the right age rocks, where you'll have dinosaur fossils in them, and that's not everywhere on Earth. But it's a lot of places. Yeah. Jody Fish says, one of my undergrad geology professors studied mid-ocean ridge basalts extensively. Very cool, Jody Fish. Very, very cool. Yeah.
The Atlantic, North Atlantic is closed, and a point of interest is that Iceland did not exist at this time.
Iceland has always been something of a mystery, with its geysers, hot springs, and boiling mud.
I love the way that Britons pronounce geyser, with its geysers. I'm sure geyser sounds funny to people from the UK also, but we say geyser here in the States.
With its geysers, hot springs, and boiling mud.
Call old people that. Treat them with respect.
Armed with the new ideas about geology, a team from Imperial College London has been doing a survey.
Well, Iceland is one of the few places in the world where one can observe seafloor spreading in action. This is because it sits astride the mid-Atlantic ridge, which comes up here and passes through the island like this. Now it enters Iceland on the Reykjanes Peninsula here, and it follows the line of post-glacial volcanic activity which crosses Iceland and splits here into two sectors. Now we are working on the southwest corner of the island on the Reykjanes Peninsula.
Mid-ocean ridge. Yeah, exactly, Jody Fish.
What
yeah.
we're doing is
Steal
we're
it down, yeah.
measuring the distance across the rift with an instrument developed by the National Physical Laboratory. What we do is to balance pulses of light across the rift for the instrument on one side and a reflector mounted on the other. And then we measure our distance by measuring the transit time of the light pulse from one side to the other and back again.
Oh, that's super cool.
It's a little early yet to make any really definite assessment of our results, but as far as we can tell, they're certainly not inconsistent with spreading of the conventional 1 centimetre or so a year, so that in 1 million years' time, Iceland will be about 10 kilometres wider than it is now.
So Iceland changes a lot very quickly.
In the middle of the Atlantic,
which makes a lot of
the new
sense.
crust of the Earth is being formed.
I mean, shoot, wasn't there a time back in like the 60s or 70s when there were massive volcanic eruptions happening in Iceland, and they had to take drastic measures to stop like a harbor from being closed? Let's see if I can find this. Yeah, take a look at this.
At 1:55 on the morning of January the 23rd, 1973, 10 years after Surtsey emerged, Iceland was subject to one of the most famous eruptions of modern times.
Yeah.
After lying dormant for at least 5,000 years, a volcano on Heimaey, a small island 6 miles off Iceland's south coast, burst into life, threatening the lives of everyone in its shadow.
Jeez.
A vast river of molten lava erupted from a mile-long fissure, or cleft, in the ground, and headed for Vestmannaeyjar. The island's...
Oh, Batman Dex, thanks for being here. You sleep well.
However,
I'll see you next time.
It was moving slowly enough to give the authorities time to start an orderly evacuation of the town's 5,300 inhabitants. 6 hours after the eruption began, most of them were on their way to the Icelandic mainland, either by plane or fishing boat. Around 200 police, fire crews and rescue workers remained, but there was little they could do as the deadly lava flow and 1.5 million tons of ash engulfed much of the town, destroying 350 houses and badly damaging more than 400. Although the lava and other volcanic material had first emanated from a fissure in the ground rather than a mountain, after 2 days it began forming a huge cinder cone. As the cone grew, the lava started flowing from its summit. By the end of February, the cone had reached a height of 600 feet and was expelling a torrent of lava and rocks up to 100 feet deep.
Jeez, wow.
As the inhabitants of Jaime helplessly watched its terrifying onslaught, they named the cone Eldfell, or Fire Mountain.
Appropriate name. And that's interesting, Chris T.S.
A few weeks later, as the great 1,000-yard-wide river of lava, moving at between 3 and 9 yards a day,
check this out.
looked as if it might reach and destroy the fishing harbor, the main source of the town's livelihood, something had to be done.
So what did they do in order to try and stop the harbor from being destroyed? Does anybody know? Adapt, says Ash Rubber. I mean, well, they could be a bit more proactive than just that. They called the Avengers, says Mayor of Space. Yes, Avenger torpedo bombers, carrier-based from World War II. No. Tried asking really nicely. They diverted the flow. Jim says, fire hoses. Yeah, they wrote a stern letter to their representatives, says Tyler. Well, maybe they did in order to get the representatives to do this, but take a look.
So, in a desperate...
Sacrifice Joe. That's one of my favorite movies of all time. No kidding. Who typed that in? Emeleth, Joe versus the Volcano. One of my favorite films of all time.
attempt to stem the deadly flow.
Here we go.
Seawater was
Fire
sprayed
hoses.
onto the river of molten rock to try and solidify it, or at least divert its relentless progress.
Yeah.
Specialist pumping equipment was brought in from the US, and a ship with the ability to direct vast amounts of water moved into the harbor. The operation, in which nearly 1.5 billion gallons of water was hosed non-stop onto the lava, using 19 miles of pipe and 43 pumps, lasted until early July 1973.
Wow.
Then it was judged a success.
See, this is
later, with the harbor saved,
this is what you can do when you actually understand geological forces. When you understand how the Earth works, you can come up with a plan for trying to save your town like this. Cool stuff. Very cool stuff.
The inhabitants of Jaime began to return. They were faced not only with a massive clear-up of their island, but they also had to set about the daunting task of rebuilding hundreds of houses and other buildings destroyed in the...
Yeah. Interesting stuff. If you want to hear more about this, I'm sure you could ask Volcano Doc. She, as a volcanologist, she probably knows a lot more about this than I do. So yeah. And that's an absurd amount of water. It is, isn't it, Galrox? Yeah. Pretty cool. Yeah. Anyway, so it turns out Iceland changes a lot.
They're certainly not inconsistent.
Pretty quickly.
With spreading of the conventional 1 centimeter or so a year. So that in 1 million years' time, Iceland will be about 10 kilometers wider than it is now.
Wow.
In the middle of the Atlantic, the new crust...
So the idea there is that Iceland is fairly new as a landmass, and it just continues to grow and grow and grow very quickly.
The Earth is being formed, and as the continents slide apart to accommodate it, the question remains, where is it going? At the other end of the world is an island which also owes its origin to tectonic activity under the sea.
Yep.
The island of Tonga in the South Pacific was the place chosen by earthquake scientists, seismologists, to investigate the deep earthquakes underneath the islands, which seemed to originate from the deep ocean trench just offshore.
Let me draw you a section through the Tonga Arc. Here we have on the surface with volcanoes, active volcanoes on top in the deep trench, and out in the Pacific Ocean. This would be the water.
It's an interesting idea, Gowrax. I don't know if that would have changed
in a zone which dips
local
down
climate.
to great depths. Now, the old idea was this earthquake zone formed, it was actually a giant fault such that the material moved down on one side relative to material moving up on the other side, shown in this fashion.
In fact, they found that tremors coming up from 60 or more miles down in the hot molten mantle reached their instruments in Tonga much earlier than their instruments in Fiji. They also found that the tremors were much weaker when they got to Fiji. The two facts suggested that the material in the earthquake zone was of a different composition, a different consistency to the material on either side. The same consistency, in fact, as the upper crust of the Earth, and it would seem that the earthquake zone and the ocean floor were all part of the same conveyor belt.
Yep, that's a subduction zone, baby. Pretty cool. And Volcano Doc can tell you all about this again. Chris T.S. says there's a clip of the Tonga eruption last year from space. Pretty incredible. Volcano Doc has studied that and published on it, and she can tell you all about it. She'll be streaming next, maybe on Sunday? Somebody look into what her streaming schedule says. I think she streams on Sundays. But make sure you check out her channel. Give her a follow right now if you want to hear more about this. Like a working scientist who's actually published on the eruption in Tonga and how volcanoes work. That's what she's all about. So check her out.
This then is a very convenient way to get rid of material created at the mid-ocean ridge system. We have material moving along here, bending over and descending into the mantle as a coherent slab.
The next major step was taken by a very young geophysicist from Cambridge, Dan Mackenzie, who provided a theory which tied together all the loose ends and formed the basis of a revolution in geology.
Well, I was sitting in the library at Scripps in Southern California reading an article by Sir Edward Bullard on the fitting of the continents, and it seemed to me that it was impossible to do this unless the continents, like South America or Africa, had remained rigid during their motion and had come together like that without any internal deformation at all. And what's more, it also seemed equally obvious that
and the biologist
also had to remain rigid.
See you later. Thanks for being here. Good luck with your class.
Magnetic lineations which have been formed on the ridge, and these had not got broken up during the motion. So we then thought, well, perhaps the whole world consists of just a series of rigid interlocking plates, like a mosaic. So on this view, the place to look for plate boundaries and where the motion is and the deformation was where there are earthquakes. And we went, then we got hold of maps of all the earthquakes of the world and looked to see where they were. And they follow the most dramatic narrow lines all over the world. And these, we decided, would be the plate boundaries. This is where there would be deformation and not elsewhere. So if we make this into a series of plates, then you can see that the...
you gotta love the age before computer graphics. They had to get creative with stuff. I love the hands-onness of that. That really appeals to me. I like that a lot.
Along the margins of these colored plates. The big ones are the Pacific plate, which consists of the whole of that region, the Atlantic and American.
I'm sure these have been revised significantly since then. Like, I'm sure it turns out to not be quite this simple. There are probably subplates within here. Like, for instance, there's the Juan de Fuca plate, which is off the coast of California. Yeah, that would be over here. So it's not quite this simple. This giant Pacific plate like that, this is actually made up of a few smaller plates, I believe. But yeah.
and various other
Thank you,
ones
Claire, for trying to look that up.
Africa
I appreciate that.
in Australia. And these are in relative motion, and where you've got a ridge, they're pulling apart, like in the South Atlantic, and creating new seafloor with its magnetic lineations. Where one plate overrides the other, the plate doesn't immediately vanish, but breaks up as it goes down into the mantle and causes and produces intermediate and deep focus earthquakes, which you only find where the plates have been destroyed, like up.
And Jody Fish says the Juan de Fuca plate is so close to full subduction that it's being occluded by the earthquake. Oh, that makes a lot of sense, Jody Fish. So it's almost completely subducted then. Oh boy. Okay, that makes a lot of sense. It's because of the Juan de Fuca plate subducting underneath the North American plate that we have things like the Coast Range here in California, including right up here. This is a live camera from Berkeley, California, way up on the hill there. And yeah, we would not have stuff like the beautiful Berkeley Hills and the Oakland Hills were it not for the Juan de Fuca plate plunging underneath the North American plate. So, pretty cool.
In the Aleutians and down past Japan. But in parts of the Eastern Pacific, like in California, the Pacific is just sliding past the American plate and is not overriding or underriding, but just sort of sliding sideways.
Yeah, I think now that's no longer true. We know about the Juan de Fuca plate subducting underneath.
It's not easy to photograph because the plates are so enormous. And even if you do it from a satellite, all the plate margins are underwater, so you can't really see what's going on there. So the best...
Freelancer wants to see the Mauritius, Africa continental shelf? I mean, sure, we can try and look that up. Yeah. There we go. That should work for you there. But yeah, that should be, I think, one of those plate boundaries right there. Pretty cool. So, east coast of Africa, Madagascar, and the island of Mauritius. This is where the dodo bird is from. Yeah. Anyway. Cool stuff. I don't know much else about this, but there you go, Freelancer. Yeah. Yeah.
Analogy we could get was with ice.
Aerial photographs of large expanses of the Arctic show how the ice forms itself into plates. Where these plates pull apart, water forms new ice in the gap, and where they're pushed together, they override each other.
And this is exactly like what goes on in the Pacific, where...
That's interesting, Nell. I didn't know about that. Dwarf humpback whale?
The Pacific plate is being overridden by the American plate up here, producing these earthquakes.
Pretty cool stuff.
Alaska in 1964, just such an earthquake struck. It was actually filmed by a sailor on board this ship. They, of course, had no notion of what was happening to the crust of the Earth several miles under their feet. Suddenly, the harbour emptied itself of water as the surrounding territory leapt in the air.
Holy cow.
Just as suddenly, the water came back in the form of a tidal wave, smashing everything in its path.
Jeez. Yowza. It's crazy that they got that on film.
Scientists had no idea why such earthquakes occurred in this region. Now, they realize that this is simply a boundary where two giant plates are overriding each other.
Crazy. Look at that.
When the Alaskan earthquake hit seismometers thousands of miles away, it practically wrecked the instruments. But it did provide a great deal of information about the movement of the two plates concerned. These instruments are connected directly to the Lamont Observatory, where one of the world's leading seismologists, Dr. Lynn Sykes, has invented a method for confirming accurately the direction the plates are moving. The cause of an earthquake is simply a slip or fault in underground rock. Can we tell what way these rocks are moving?
Yes, the basic principle in determining a fault plane solution for an earthquake is that if we imagine that there is a
9.2 megathrust earthquake. That's crazy,
Jody.
Jody
A map
Fish.
view.
Holy
if this
cow.
side moves to the north and this side moves to the south suddenly during an earthquake, what we find is that the first motions of the P waves are such that stations in this quadrant receive compressions or outward first motions. These over here, dilatations or inward motions, dilatations and compressions. In other words, the first motions are divided into 4 different quadrants. By mapping these quadrants, it's possible then to determine the orientation of the
pretty
fault
neat.
and the direction of motion on the fault. These are
600 miles of crust moved 60 feet during the quake. That's really crazy, Jody Fish. Holy cow.
The seismograph instruments that we operate at Lamont. In fact, you can see an earthquake that was recorded about 3 hours ago. There's a very clear upward motion of the P wave on this record. We need more information than this, however, if we're going to examine the complete details of an earthquake.
In fact, a worldwide network for earthquake information was set up by the American government for the detection of nuclear explosions. It now
during
provides
the Cold War.
scientists with even more information than they need. Seismic stations around the globe report the arrival times of every single earthquake, large or small.
Look at these cutting-edge computers in
More likely to a
1970.
comprehensive picture. The date, time, exact location, depth and magnitude of each event are given, together with the first motions. So earthquakes have given us not only the boundaries of the plates, but also the relative directions in which they move. So much information is now available that a young research student from Los Angeles has built a sort of globe to test whether the movement of the plates matches the original hypothesis all around the world.
Very cool.
It shows much better than you can on a flat sheet of paper how...
And squelch the noise. Welcome to Paleontologizing. Good to have you here. Do you know that plate tectonics are one of the contributors to global... I don't think that's right. Friction causes heat, and we're just... Also, I just say things clearly. Welcome. It's good to have you here. Thank you for that disclaimer at the end. Welcome to Paleontologizing. It's good to have you here. How are you doing? Welcome. And what a globe is that? That is super cool, isn't it? Yeah. Talk about pre-computer modeling. That globe is awesome. Isn't it, Steely Dan? Pretty neat.
To test whether the movement of the plates matches the original hypothesis all around the world.
It shows much better than you can on a flat sheet of paper how the various plates move. If you take the boundary between South America and Africa, this is the way it looked 20 million years ago.
I think you're going to feel right at home around here, I hope.
It's closed up. And then if you go forward in time to today, it opens up a little bit. Now, on the other hand, if you go around over here to the Pacific, this is the way the East Pacific Rise looked 20 million years ago, and this is the way it looks today. See, it opened up a lot more than the Mid-Atlantic Ridge did, just the way the magnetic anomalies show. And here in the Tonga Trench region, this is what it looked like 20 million years ago. And if you go forward in time, you can see how it closes up, just as it closes up along the that side of the Pacific Ocean over there. One interesting thing to look at also is here in the vicinity of India. Here 20 million years ago, India was much farther south. And if you go forward in time, you can see how India crashes in to the southern part of Asia.
Drives up the Himalayan mountains.
The plate tectonics theory, only published 2 years ago, has already had an enormous impact. Even the Gemini astronaut pictures of the Red Sea and Aden show clearly how 2 plates here once fitted closely together.
Very cool.
But it's the earth sciences which have been knocked sideways, in particular the fields of earthquakes, volcanoes and mountain building. What happens, for example, when continents collide?
Let's imagine, for instance, this is India, perhaps 100 million years ago, and the Asian continent, when there was once an ocean between the two. This is the old Tethyan Ocean. And what I've done here is to move India northwards, progressively northwards, and gradually push all these sediments which lie on the bed of the ocean and squeeze them in a vice-like fashion and produce the Himalayas. And we can take it one step further and have the present-day situation in which the Indian shield has gone down underneath the Tibetan shield and has doubled up the thickness of the crust, with the Himalayas sitting on top of the system.
Pretty cool.
If this is the result of plate collision in the past, can scientists tell us what mountains will be built in the future?
Well, what we think, one of the interesting areas is the Mediterranean here, where we think what's going to happen is what has happened in the past along northern part of India. This is an enlargement of showing that where the earthquakes now are in the Mediterranean region. And what's now happening is that Africa is moving northwards towards Europe, and that the Mediterranean is being underthrust beneath the Cretan Arc all the way along here. And presumably, what's going to happen later on is that mountains are going to get built out of the sediment that's now in the Mediterranean.
So the Mediterranean will close up and become a mountain range far, far, far into the future, millions of years from now.
The new
hey, Pfizer, welcome. Good to have you here.
In the Mediterranean is, of course, producing the volcanoes and earthquakes in that area. But in Northwest America, the volcanoes in the Cascade Range are on the decline, or so everyone thought. It's now believed that the remains of the plate which built the volcanoes may still be descending underneath them.
Yep.
This has sent scientists scurrying up to the edge of the craters to find out what's going on.
Is this Mount St. Helens?
Because the volcanoes were thought to be extinct, large towns like Seattle and Portland have been built close by. It's now known that these towns will be wiped out. It may not be until man has moved to another planet, but it will happen.
Oh boy, I hope nobody's watching from Seattle or Portland right now. Oh boy. Yeah. And this is before the Mount St. Helens eruption. Now, Mount St. Helens was, I think, 1980. This is 1970. Yeah. Yeah.
This volcanologist from the University of Oregon has instruments set round the rim of Crater Lake. He's trying to find out what's happening far below at the volcano's roots.
Mount Baker, yeah, there you go, Van Bucan. Van Bucan?
When you think of
Van
eruptions,
Bucan?
people used to think, and mostly think of the hazard as it relates to volcanoes like the Hawaiian volcanoes, but you must realize that these volcanoes are of a quite different type. And if we have an eruption, it's much more apt to be the very explosive, the very violent type. We might even
like Mount St.
be
Helens.
able to see something like the
This is
creation of
prescient here.
meteorites, where material is mixed with water and it comes pouring out of the volcano at a very high temperature. It's so hot, in fact, that it is actually in particles, but after it settles, it re-glues together and re-welds. This forms a welded tuff or an ignimbrite, and although there's tremendous areas of this in the United States, there have never been any eruptions of this type, but we have volcanoes that are not of the Hawaiian type, but of the more dangerous type. As a matter of fact, we get several earthquakes a day, and this seems quite a bit higher than we would expect to find from a region that's inactive. And as a matter of fact, this whole study is exciting because it's the geology of now. Lots of times we can look at the rocks and say this happened in the past, but with geophysics,
There you go, Neverwinter, yeah. Cool, right?
Earthquake study,
Sculpin, how you doing? Welcome,
because
welcome.
it tells us what kind of tectonics, what kind of adjustment is the Earth making right at this minute.
And wait, HD says, so when they say Yellowstone won't explode for 1 million years, we're hosed? No, I mean, Yellowstone is something totally different. Shoot. It's like Volcano Doc said during the panel. Let me find that quote of hers, actually. Here. I'm sure I can find it by going back to my Twitter. But, yeah, where was that? There we go.
Yeah, and I also play, oh, sorry.
Um,
I'm actually a high school dropout, and I got pregnant in high school and worked my way up, and I like to
share that story because I know that not enough people have opportunities that like we were so lucky to have.
That's Volcano Doc there speaking.
Half of it is luck. And I want to provide people a place where they can come in and just genuinely
Check her out if you're not yet following Volcano Doc.
not feel bad about them.
Make sure you do.
It's so important that we as scientists
One of our best science communicators on Twitch right now.
know everything, and I will be the first to say, oh, I don't know, and I will also admit when I'm wrong. And I love doing that on stream and showing you that, yeah, I mean, I have an education, but I'm not infallible at all. And I sure don't know a lot of stuff. I can barely work a remote. So.
And yeah, Pfizer, Yellowstone is a caldera rather than like a shield volcano or something like that.
Have a space.
But she talks about that. Here we go.
If Yellowstone, when Yellowstone erupts, not if, when, it will more than likely be a small lava flow. I can't say there wouldn't be a super big, explosive eruption. There's always that tiny chance, but more than likely, it would be very, very small, not super explosive, and I promise you that, like, you can't cough at Yellowstone without it being recorded. The seismometers actually were able, they kind of went quiet and you could detect tourist activity on them. So you could see that during the pandemic. They're that sensitive, and we genuinely just have your, like, safety. That's all we want. So, like, we will tell you everything. Like, trust me, we can't like hold stuff back. We're bad. I'm a bad secret keeper. Like, I would say something. Fantastic.
Yeah. So anyway, but on the other hand, talking about the volcanoes in the Pacific Northwest, like Mount St. Helens, this guy is like, yeah, we're seeing activity here. Like, these are not inactive. Like, ew. And yeah, before the Mount St. Helens eruption, there were warnings that went out to the public, like, stay away. It's doing something weird. There's this big bulge that's appearing on the side of the volcano's exterior. Like, they knew that something was up, and they tried to evacuate people, but some people just didn't listen, you know? Yeah.
It tells us what kind of tectonics, what kind of adjustment is the Earth making right at this minute.
It's in the various earthquake-plagued areas of the world that it becomes really urgent to know what's going on.
Yeah.
One of these is California, where the famous San Andreas Fault runs in a straight line for hundreds of miles.
Yep.
Sometimes it's clearly visible, sometimes it's lost in the hills and valleys. But it also passes through areas of extremely dense population. From Los Angeles, it runs north, smack through the village of San Juan Bautista, and on into the San Francisco Bay Area.
The where? The beautiful, sunny San Francisco Bay Area? Yes, indeed. The San Andreas Fault runs just... These are like the Marin Headlands right here. It's just over there in the Pacific. It runs right along there. So on the other side of the bridge. Yeah. Diagonal says, I used to live on the Hayward Fault. Yeah, the Hayward Fault is that direction over there in Hayward, Oakland, etc. And I lived pretty close to the Hayward Fault. I even live streamed the Hayward Fault back in 2021 when I was on the campus at UC Berkeley. Some of you may have been here for that live stream. It was a lot of fun. But we were like tracing the Hayward Fault as it ran through campus. You can see like cracks in the pavement and stuff like that, and then it goes right through Memorial Stadium in Berkeley. So, yeah.
In terms of plate tectonics, this line is a boundary between two plates, which are sliding past each other.
Neverwinter says, I hope your house is built to code. I live in a big apartment building, Neverwinter, and hopefully it's built to code. But I have to move out in December, so... yeah, cross your fingers that where I'm going to be living next is also earthquake safe.
One of the edges of the world.
Well, here we can look across the San Andreas Fault that occupies the trough under the lake toward the hills in the distance, which are on what, in a grossly oversimplified way, could be called the Pacific Plate. Now, that extends from here on out for thousands of miles into the Pacific Ocean. Where we're standing, we're on what could be called the North American Plate that extends thousands of miles out into the Atlantic Ocean. Now, that side opposite, these two plates, of course, are moving with respect to each other, and that has moved something like an inch a year for millions of years. And here in the foreground, we can see a variety of rock called the Franciscan rock that characterizes the eastern or North American plate.
Yeah, things are generally built pretty sturdy here, Gale Rocks.
On the opposite side, because
Most of the
this
time.
tremendous movement.
That's why we have regulations for this kind of
between
thing.
the two plates.
Yeah.
The region is, of course, honeycombed with seismic instruments.
Yeah.
The strain gauge is simply a wire stretched between 2 points on either side of the fault line.
That's really cool. Such a simple instrument. Look at that.
The readings are fed straight back to seismologists at the U.S. Geological Survey Unit at Menlo Park. Here, every tiniest tremor, every micro-earthquake is monitored. Sometimes as many as 50 a day.
Wow. Two detached holes in the Echo HD,
Strain
yeah.
gauges tell them how much the two plates are moving, and the answer is an inexorable 6 centimeters a year.
Very cool. Probably about the same rate that your
These
fingernails
two
grow.
great,
Yeah.
plates move past each other. Some areas tend to
Actually, no,
lock
maybe that's faster than your
periodically and
fingernails
hang
grow.
up and then break through. And these two red segments on the fault, one broke in 1857, the other in 1906. But strangely, now those are very quiet
1906.
areas. No movement do we detect, nor do we see any small earthquakes. These other colored areas, however, are creeping and are characterized by very small earthquakes. If we take a look at this section right here near Hollister, over on this more detailed
Yeah,
map,
the
we can see
Franciscan
some
Formation. Those are really cool
mapping
rocks,
by,
Neverwinter. Yeah.
micro tremor mapping. We put out seismographs on these red triangles, and this allows us to identify very small earthquakes. And this is a set of earthquakes in a very few months' time in the Hollister area. But then look at the part of the San Andreas Fault up here in the San Francisco Bay Area. Almost no earthquakes. This is now locked, and yet we are sure that this will break again someday and perhaps produce another great earthquake.
And it did in 1989, which was 19 years after this documentary came out. I believe the Loma Prieta quake was on the San Andreas Fault. I don't think it was the Calaveras Fault or the Hayward Fault. I'm pretty sure it was the San Andreas Fault. The 1989 Loma Prieta quake. Yeah.
In 1906, half of San Francisco was destroyed, and San Franciscans today are understandably worried that it will happen again.
It did in 1989.
Scientists know that as each year passes it'll be bigger, but unfortunately they don't know when it will happen. In the same way that our view of the globe was changed by the astronauts looking back from the moon, so the new geology will alter our idea of where the parish boundaries of our globe are. Every textbook from primary school to university will have to be rewritten as scientists get together all over the world.
Yeah.
Geochemists, geophysicists, paleontologists, many people who used to work sort of among themselves, not understanding really what each other were doing, are now able to focus their efforts on to common problems, to see the significance of what they're doing in a larger picture.
Yep.
This, I think, is always good. In practical ways, it will have an impact too, and I think in the very near future. For example, with earthquakes, we now, knowing the motions of the plates, are able to understand in new ways the reasons why earthquakes are generated and the effects that they have. In more subtle ways and human ways, which are really the most exciting ways, for example, young people in the earth sciences now, once at a disadvantage and still somewhat from lack of experience and so on, lack of having been around the world and seen it all, nevertheless, with this new theory, have mental tools that are powerful enough to allow them to lunge into the mainstream of thinking and to attack important problems very early in their career.
And this is a thing, like, this is one of the things that I wanted to talk about during this broadcast today, is kind of how scientific revolutions happen. So with talking about this stuff, with like continental drift, plate tectonics, These were new ideas back in the 60s and 70s. And not everybody latched onto them immediately. There were scientists who did not want to accept the new information.
I can see that my 50,000 a year has been well spent.
And Janine's Mess, thank you for those 3 months of Tier 3 support. Thank you for being an adopter of this stream when you were and helping me continue to do this. I really appreciate that. Janine, thank you very, very much. Holy cow. Yeah. There's an old phrase in the sciences, and it's that that science advances one funeral at a time. And it's a grim way of looking at things, but in some cases it's kind of true. There were geologists who just never accepted continental drift, plate tectonics. And, well, yeah, eventually they got left behind, they died, the field moved on. There's a quote about that in a book that I have up here. Let me get that out. I've already bookmarked it. So this is a collection of several different books, actually, by John McPhee. Annals of the Former World. The book that we're looking at in particular is called Basin and Range. It's book 1 in here. There we go. And, yeah. Let's see. I mentioned that I had read in geology. There we go. Geology, that, like, kind of semi-professional or semi-popular magazine on our sites. I mentioned that I had read in geology that 1 out of 8 geologists do not accept plate tectonic theory. And this was in... Can somebody tell me when Basin and Range by John McPhee was published? I believe it was in the early 1980s. 81, I think it was. Yeah. And DeFaze, who is the geologist that the author was following around, he said, there are still a few people dragging their feet. They don't want to come into the story. The article in Geology was based on a questionnaire that was circulated toward the end of the 1970s. There we go. The questions indicated that 40% of geologists had come to feel that plate tectonics theory was essentially established, or roughly an equal number preferred to qualify a bit and say that it was fairly well established. So that's 80% of geologists saying it's either really fairly well established or like pretty well established. 11% felt that the theory was inadequately proven. Not yet proven. 7% said that they had accepted continental drift before 1940. 6% thought plate tectonics would be still in doubt in the late 1980s. And one geologist predicted that the theory would eventually be rejected. At any given moment, no 2 geologists are going to have in their heads exactly the same levels of acceptance of all hypotheses and theories that are floating around, DeFaze said. There are always many ideas in various stages of acceptance. This is how science works. Ideas range from the solidly accepted to the literally half-baked. Those in the process of forming, the sorts of things about which people call each other up in the middle of the night. All science involves speculation, and few sciences include as much speculation as geology. Is the Delaware water gap the outlet of a huge lake, and all other traces of which have since disappeared? A geomorphologist will tell you that, in principle, the idea is okay. You have to deal with partial information. In oil drilling, you had better be ready to act shrewdly on partial information. Do physicists do that? Heck no. They want to have it proven to 7 decimal places on their Hewlett-Packards. The geologist has to choose the course of action with the best statistical chance. As a result, this style of geology is full of inferences, and they change. No one has ever seen a geosyncline. No one has ever seen the welding of tuff. No one has ever seen a granite batholith intrude. I wonder if those are still true to this day. Anyway, good stuff. But yeah, by the 1980s, especially the end of the 1980s, plate tectonics had been pretty much universally accepted by geologists, and today, in the year 2023, it's essentially unanimous. You'd have a really, really difficult time trying to find a geologist who does not accept plate tectonics, continental drift. When you do find one, chances are they're, I don't know, not actually a geologist. They're like a creationist or something like that. So yeah. And McPhee, wonderful writer, Neverwinter. I agree. Yeah. That book is called Basin and Range. I highly recommend it to anybody who would love a lovely mix of kind of really strong literary prose and geology. Excellent book. Basin and Range by John McPhee. Anyway, let's close out this video.
Getting even wider and more grandiose, but I think still being true. Men at large have a better way now to understand, with no background in
people at
geology
large,
all,
I would say no.
How the world is put together and how it has gotten to be what it is. This means, in some subtle, inside the mind way, I think the ultimate long-range benefit of this kind of thinking may be to let people appreciate better what their environment really is, what kind of balances really do exist in the earth.
There you go. What a wonderful documentary from 1970. Good stuff. I'm so glad I found this morning. And again, the whole reason that we're talking about this, talking about plate tectonics, is because of Alfred Wegener. His birthday today, November 1st. He was born in 1880. His The Origin of Continents and Oceans is a really interesting work. And if you'd like to read that, here is a link to the online PDF. It's translated from the original German, but there's Alfred Wegener right there. And now I want to show you a really cool animated video about this. Kind of round things out. This really hits me in the feels. I think it might do the same for you too. So here we go. Enjoy.
Hardly anyone in the early 20th century said, why are there oceans and why are there continents?
Yep.
Wegener is a wonderful example of how science benefits from people coming from outside a scientific field and saying, well, why don't you look at it this way?
Go Jody Fish, yeah. Oh, this is great.
Getting into a balloon and going up into the air for a meteorologist is like getting into a boat and going out on the ocean for an oceanographer.
He goes up in a balloon because he wants to take measurements of the atmosphere. He's not the Wizard of Oz. He's a scientist doing science.
Yep.
Wegener flew as much and as often as he could. He wants to write the best book on the physics of the atmosphere, and no one had ever studied the atmosphere in the high Arctic before.
This is a time in history when one of the most exciting things you can do as a scientist is to go on an Arctic expedition.
It was adventure travel of a North Pole, South Pole kind. Wegener's out there in the winter night taking these huge box kites and attaching recording instruments to them and then winching them back down to get his instruments back.
Incredibly cold there, HD. Incredibly
Nobody
cold.
ever said that Arctic exploration was a picnic.
Wegener had to learn how to hunt seals, how to drive a dog sled, how to travel on ice without being swept into open water, how to protect your dogs from polar bears. The travel in Greenland, his time with icebergs,
The way in which the ice flows form jigsaw puzzle pieces.
the way the ice cap splits apart and fissures. All of this was part of his imagination when he made his discovery of continental drift.
I wouldn't really call it a discovery. What he really had was an idea.
He went to his office, and his office mate said, "Look at this beautiful atlas my parents gave me for Christmas." And he wrote to his fiancée, "Did you ever notice how South America fits into Africa?" Let me pause and say, there isn't a child on Earth over the age of 12 who hasn't had the same thought, right? You can see it.
Yeah.
What was different about what Wegener saw? There were lines on the map that represented depths under the water, and they're exactly the same shape. That means that this is part of the structure of the Earth. How did that come about? Maybe the continents drifted apart.
It was radical because it was new. The Americans say the continents are fixed. Europeans think they move, but they think they move up and down. And Wegener says you're all wrong. Yes, they move, but they move horizontally, not vertically.
Pretty groundbreaking stuff. Clipper, yeah, let me give you a link to the other one. That was... Shoot, give me a second here. Let's see. Open. Copy. There we go. And let's see. I believe Dino Wolf was also asking about dinosaur documentaries, and there is here we go. A really excellent YouTube channel. There's a YouTube channel where someone has compiled a whole bunch of different dinosaur documentaries. Some of them quite old, some of them fairly new. And so, Dino Wolf, enjoy this. Hopefully some of those ones that you haven't been able to find will be there, and you'll be able to watch them. Yeah. Good stuff. Good stuff. There's our video. There we go.
Are fixed. Europeans think they move, but they think they move up and down. And Wegener says you're all
roll over
yes,
in place.
They move, but they move horizontally, not vertically.
He would write a paper in 1912, and he said, "I think everybody will really be happy." And of course, everyone wasn't really happy. Everyone became very unhappy.
There was a almost universal rejection of his theories to begin with.
Yeah.
Here's the problem. Scientists are very suspicious of fundamental novelty.
Yeah, it's true.
He was regarded as an outsider by the geoscience community because he had no academic credentials in that field, and so he was not considered qualified to make any statements in that field.
And this is the thing, like, when, as a scientist, if someone from another field comes in and they go, "Yeah, I think all of you guys in your field are all wrong. I'm not trained in your field, but, you know, I've got some wild idea about something." Like, that kind of happens with fair frequency. And usually those people, they're crackpots. That wasn't the case here. Wegener was really onto something. And nobody really had any good ideas about why the continents looked the ways that they did, why they looked like they should fit together like puzzle pieces, all that stuff. Oh, yeah. Yeah.
What he was doing,
and there you go, Lenina. Yeah, that's the
thing.
thing.
Drawing together multiple lines of evidence, not just geology, but vegetation and paleontology.
Yep.
Hello. The creature we will be examining is a paleontologist.
And Vedator CZ, thank you so much for the raid. Welcome to Paleontologizing. How are you? And how did your stream go? I hope it was real good. Welcome back. We are celebrating the birthday of the father of continental drift, Alfred Wegener, born on this day, November 1st, 1880. He had this idea that the continents actually were not stationary, but that they moved slowly over time. People laughed at this idea originally. Later on, years after his death, he was vindicated. Nowadays, we recognize that the continents move, and it explains so much about the history of life on Earth, about the shape of our continents today, about earthquakes and volcanoes and, you know, so many fundamental processes of the Earth, like they're tied back to the continents moving. Pretty cool. So anyway, you came in at a good time because we were just watching this lovely video. Here, I'll scoot back a little bit. Right here. Yeah.
Maybe the continents drifted apart.
It was radical because it was new. The Americans say
Anyway,
the continents are
Vedator, I hope you had a great stream. Tell me about how it went. And welcome back to Paleontologizing.
It was radical because it was new. The Americans say the continents are fixed. Europeans think they move, but they think they move up and down. And Wegener says you're all wrong. Yes, they move, but they move horizontally, not vertically.
He would write a paper in 1912, and he said, I think everybody will really be happy. And of course, everyone wasn't really happy. Everyone became very unhappy.
There was a almost universal rejection of his theories to begin with.
Here's the problem. Scientists are very suspicious of fundamental novelty.
Yep.
He was
We are.
regarded as an outsider
with good reason.
by the geoscience community because he had no academic credentials in that field, and so he was not considered qualified to make any statements in that field. What he was doing that was so different, though, was drawing together multiple lines of evidence, not just geology, but vegetation and paleontology.
Yep.
The botanical people
Paleontology.
responded very positively because it explained the distribution of plants and animals over the world.
Paleontologists also were very receptive to this idea from pretty early on. Because it works really well with the fossils. I mean, shoot, it helps explain why you find the same fossils on the east coast of South America and the west coast of Africa. Why you have the same, like similar kinds of fossils going from Australia down into Antarctica and then down into the southern tip of Africa too. It just made sense from a fossils perspective. Yeah. And when an idea in science fits well with the evidence, then you might have something there. That's the thing. And unlike other people, I don't know, lawyers or theologians or philosophers, where they're trying to take the facts and get them to fit into whatever narrative they have. It's like, no, in science, it's the opposite, We tailor our narrative to what the facts are, what the evidence actually is. And yeah, the evidence from fossil science worked really well with this idea that the continents moved.
In different places on Earth.
Yeah, Listersaurus and Glossopteris, exactly, Neverwinter, yeah.
Fossil.
They're going to show those here.
The stratigraphic columns were extremely similar as well. And Wegener's idea, his big idea, was you could explain all of those things if the continents had moved.
So he would write a book in 1915. People said, well, this is wrong and that's wrong. And then he wrote another book in 1920. He comes up with the name Pangaea. And then he wrote another one in 1922. And he kept fixing it and fixing it and fixing it. It's one thing to think of an idea, and it's another thing to work it out for 20 or 30 years.
Yep.
That book's still available on Amazon.
And there you go, Steely Dan. That does make sense. GPS system.
Continental drift was something he was interested in, but it was never the focus of his scientific life.
The Arctic pulled him back in. He was really too old, almost 50 years old.
Linnaeus says it's so tragic that he didn't live to see his ideas become mainstream. Dude was a genius. I mean, maybe he would have lived to see his ideas become mainstream if he hadn't been such an intrepid individual. I mean, one of the reasons why he is a legend is because of what happened next.
Landed there with 98 tons of equipment.
And from the beginning, things didn't go well.
They had many things go wrong.
The base in the middle of the ice cap did not have enough food, and he said, this is my responsibility to resupply.
And he got several sleds together.
It's the worst conditions you can possibly imagine. His companions wanted to give up. And at twilight, Wegener said, let's go for a walk. He took them out and pointed to the ice and pointed to the sky. And
I love this part so much because this, as a scientist, this gets me right here.
Said, "We're trying to find out how all this works. It doesn't matter whether we live or die. The important thing is that the work go on."
And I guess that's why I love Alfred Wegener, because it's not really about himself. It's that he believes in science, a kind of great metaphorical expedition.
At the end of all this, they were able to supply the station at the middle of the ice, and then they got there, and there wasn't enough food to last the winter for all of them. Wegener said, "I'm going to go back to the coast." He didn't like to ride on the dog sled. He liked to ski next to the dogs. He had a heart attack and died. He's still there. The German government wanted to bring him back for a big funeral, and his wife said, "No, leave him there. He's where he wants to be."
Yep. What a beautiful video.
What he was wrong about was the physics of it, and he thought it happened way too fast. Here's what he got right. The continents move. They really do.
And in fact, are still moving today.
We can measure that movement.
At that time, the land and the planet was clumped together in one vast supercontinent.
Well, look at that.
Dinosaurs soon occupied every corner of that world.
Perfect timing there.
Hello, sorry,
Cast me out black. Thank you for those 4 months of support. And what a perfect alert for that very moment right there. As a dinosaur paleontologist, continental drift is one of those things that it's fundamental to the history of the Dinosauria. Dinosaurs start off, they first evolve when the continents are stuck together like this. That's the reason why we have dinosaurs on every continent on Earth, including Antarctica. It's because when they first evolved, actually let's go back to 240 million years ago. There we go. Even better. You could basically walk to any corner of the globe, you know, at least in terms of dry land. And later, as the continents drift apart, as those plates float on the Earth's mantle, further and further apart, they take dinosaurs with them. And you get interesting groups of dinosaurs that evolve on different continents. You get different dinosaurs down here in Gondwana, the southern continents, South America, Africa, India and Madagascar, Antarctica and Australia. Different ones there than you get up here in Laurasia, North America, and Europe and Asia. And at various points in the history of the evolution of dinosaurs, you see dinosaurs make the trip from Europe and Asia into North America and vice versa. And you get these like pulses of migration when there are land bridges that form there, when the sea levels drop to the point where you can actually walk in between. And this influences the evolution of dinosaurs. That's something that Jim Kirkland is currently studying in the Cedar Mountain Formation. Super interesting stuff, and it all ties back to Alfred Wegener. He was ahead of his time, a true man of science, and even though he maybe was not vindicated during his lifetime, today we all celebrate the foresight that he had and the way that scientists from around the world have demonstrated that his ideas were at least partly correct. The continents do move. And I think that's a wonderful legacy for a scientist to have. To have your ideas later confirmed by new methods, new evidence, and new scientists. So on that note, we're going to wrap this thing up for today. Let's put a Deinonychus there to run our credits over. And we're going to see who else is streaming on Twitch right now. Tomorrow, well, I'll tell you what we're going to do on tomorrow's stream in just a minute. But first, let me find somebody to raid real quick here. Thank you again to everybody whose names are showing up here in those credits. Let's see here. We're going to go raid into Science Streams. Yeah. Thank you to everybody in the credits. Followers and gifters and lurkers and cheerers and moderators and everybody else. Question askers, enthusers, viewers of all sorts. Thank you for helping me do what I do here. I appreciate you more than you know. It's a privilege to be able to bring science to you every weekday. Thank you for helping me do that, all of you. On tomorrow's broadcast, we'll be doing Thursday Birds Day, like we usually do on Thursdays. And I'm also going to be doing a dinosaur deep dive marathon. We've got a bunch of dinosaur deep dives that have been accumulating, not just today, but over the past few weeks. We've got, what, Giganotosaurus and Rebbachisaurus, and Mayor Space redeemed one today. Was it Homalocephali? We'll also be talking about that new mosasaur that people have been asking me about also. So until then, everybody, you all take care of yourselves. I hope to see you tomorrow, and I hope to see you right now in Science Streams channel. All right. Take care, everybody. Bye-bye. See you soon.
And we could have a conversation with Parrot.
That's